The universe is not crowded, it is abandoned. Right now, at this very moment, 2 trillion galaxies are scattered across observable space like grains of sand in a cathedral the size of infinity, and every single one of them is alone. Not metaphorically alone, not poetically isolated. Actually, physically, mathematically separated by distances so vast that even light, the fastest thing nature allows, takes millions of years just to cross the gap between neighbors. The Andromeda Galaxy, our closest major companion, sits 2.5 million light-years away. At the speed of light, you could lap the Earth 7 times in 1 second. You could reach the Moon in a heartbeat, but Andromeda, 2.5 million years, and that is just next door. Because here is what no one tells you about the cosmos. The galaxies are not the universe. The emptiness between them is. 80% of all observable space is void, not mostly empty, not sparsely populated, void. Hundreds of millions of light-years of nothing. No stars, no gas, no dust, no planets, not even dark matter in any meaningful quantity. Just distance, stretching in every direction, separating island from island in an ocean that will never be crossed. We have catalogued 2 trillion galaxies. We have mapped the large-scale structure of reality itself. We have peered back to the edge of time, and what we have found is this. The universe is not a place where things are close together. It is a place where things are impossibly, permanently far apart, and expansion is making it worse. Every second, the voids grow wider. Every moment, more galaxies slip beyond the horizon of what we could ever reach, even in principle. This is the true scale of intergalactic space. And this is why we are alone. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From nearby starlight to the oldest visible glow, we will chart the structures hidden within the intervals between galaxies. Then, at the edge of the possible, we will ask which shores remain open and which are already leaving us behind. You are here, right now, sitting on a planet that is spinning at about 1,000 miles per hour, orbiting a star at 67,000 miles per hour, inside a galaxy that is hurtling through space at roughly 500,000 miles per hour, and you feel none of it. Not a tremor, not a breeze. The coffee in your cup sits perfectly still. The ground beneath your feet feels solid, motionless, as if the entire universe has agreed to hold its breath while you go about your day. That stillness is the first lie the cosmos tells you. The second lie is proximity. You look up at the night sky, and the stars feel close, reachable, almost. A child's drawing of the universe would scatter them evenly across a dark page, little white dots sprinkled like sugar. That drawing would be catastrophically wrong, but it would feel right because that is what the sky suggests. A neighborhood, a crowded one. The truth is that the space between those dots is so large, so incomprehensibly empty, that if you tried to build a scale model of even our local cosmic neighborhood, you would run out of Earth before you ran out of space to represent. Let's start small. Let's start with the one address in the universe you can actually write on an envelope. Earth, third planet from the Sun, roughly 8,000 miles across. Home to 8 billion humans, most of whom have never seriously considered what it means to live on a ball of rock flying through an ocean of nothing. The Sun, our nearest star, sits about 93 million miles away. That distance has a name. Astronomers call it 1 astronomical unit. It is the ruler by which we measure the solar system. Light from the Sun takes about 8 minutes to reach us. If the Sun vanished right now, you would not know it for 8 minutes. You would keep living, keep scrolling, keep breathing under sunlight that was already a lie, already the ghost of a star that no longer existed. That 8-minute delay is your first real hint that distance in the universe is not just big, it is functionally hostile to human intuition. Pluto, the farthest recognized object in our classical solar system, orbits at about 40 astronomical units, roughly 3.7 billion miles. Light from the sun takes more than 5 hours to reach it. If you tried to drive to Pluto at highway speed, it would take you about 6,000 years. If you sent a radio signal to a probe sitting on Pluto's surface, your message would arrive 5 hours later. The reply would take another 5 hours to come back. A 10-hour round trip for a conversation with a machine parked in our own backyard. And Pluto is nothing. Pluto is the front porch. The solar system does not end at Pluto. It ends, arguably, at the edge of the Oort cloud, a vast shell of icy debris left over from the formation of the Sun, stretching out to somewhere between 1 and 2 light years from the center. That is not a typo. Light years, not astronomical units, not millions of miles. A light year is the distance light travels in 1 year, moving at 186,000 miles per second. It is about 6 trillion miles. The Oort cloud, the outermost boundary of the Sun's gravitational influence, extends roughly halfway to the nearest star, and it is empty. Almost perfectly empty. A few trillion chunks of ice drifting in the dark, separated by distances so vast that if you stood on one, you would not see the next one, even with a telescope. The nearest star to our Sun is called Proxima Centauri. It sits 4.2 light-years away. If the Sun were the size of a basketball sitting in the middle of a football field, Proxima Centauri would be another basketball sitting somewhere in the next state. The fastest spacecraft humanity has ever built, Voyager 1, is currently moving at about 38,000 miles per hour relative to the Sun. At that speed, it would take roughly 70,000 years to reach Proxima Centauri. 70,000 years. That is longer than recorded human history, longer than agriculture, longer than cities, longer than writing, longer than everything we would recognize as civilization. And Proxima Centauri is right next door. Now zoom out. Our Sun is one star among something like 200 to 400 billion stars in the Milky Way galaxy. The exact number is not known. You cannot count them. Most of them are too faint, too distant, or hidden behind clouds of gas and dust. But the best estimates, stitched together from decades of observation and modeling, land somewhere in that range. 200 billion on the conservative end. 400 billion if you are feeling generous. Either way, the number is incomprehensible. If you tried to count every star in the Milky Way at a rate of 1 per second, never stopping, never sleeping, it would take you more than 6,000 years, and that is just one galaxy. The Milky Way is shaped like a flat disk with a bulging center, spiral arms curling outward like cream stirred into coffee. From edge to edge, it stretches about 100,000 light-years across. Our Sun sits out in one of the spiral arms, about 26,000 light-years from the galactic center. If you could somehow hover above the Milky Way and look down at it from outside, you would see a glowing pinwheel of stars, gas and dust, rotating slowly, one full turn, taking roughly 200 million years. The Sun has completed that journey around the galactic center only about 20 times since it formed. Dinosaurs walked the Earth the last time we were on the opposite side of the galaxy. That is the scale we are working with, not decades, not centuries. Hundreds of millions of years just to go around once. At night, when you look up and see that faint band of light stretching across the sky, that is the Milky Way. You are looking at the combined glow of billions of stars in the disk, most of them too far and too faint to resolve individually. You are seeing the inside of your own galaxy from within, the way a fish might see a river if it had the capacity to look around and notice the water. And here is the thing that almost no one pauses to think about. Every star you can see with your naked eye, every single one, is in the Milky Way. Not some of them, all of them. The human eye, even on the clearest, darkest night far from city lights, can only resolve about 5,000 individual stars, and all 5,000 of them are local. Most are within a few hundred light years. The farthest naked eye star, Deneb, sits about 2,600 light years away. Still inside the Milky Way. Still, by cosmic standards, right next door. When you look up at the night sky, you are not seeing the universe, you are seeing your neighborhood. There is one exception, one object visible to the naked eye that is not part of the Milky Way. It shows up as a faint smudge in the constellation Andromeda. For most of human history, it was catalogued as a nebula, a cloud of gas. In 1924, Edwin Hubble, working with the newly completed Hooker telescope at Mount Wilson Observatory, resolved individual stars within that smudge and proved that it was not a cloud, it was another galaxy, separate, distant, enormous. We call it Andromeda, or M31 if you are reading an astronomy catalogue. It is the closest large galaxy to the Milky Way, sitting about 2.5 million light-years away. That distance deserves a moment of your attention. 2.5 million light-years. The light you see when you look at Andromeda left that galaxy 2.5 million years ago. Humans did not exist yet. Our ancestors were barely upright. The photons that hit your eye tonight began their journey across empty space long before anyone was around to name the stars, to build cities, to wonder where the light came from. You are not seeing Andromeda as it is. You are seeing Andromeda as it was when the Earth was a colder, stranger place, populated by creatures that would eventually, slowly, improbably become us. Andromeda is larger than the Milky Way. It contains roughly 1 trillion stars, more than twice what our galaxy holds. If you could see it in its full glory, not just the faint core that shows up in photographs, it would span about 6 times the width of the full moon in the night sky. But most of it is too faint to register without long exposure imaging. What you see with your eyes is only the bright central bulge, a concentrated knot of old stars glowing dimly at the heart of something much, much larger, and it is coming toward us. Andromeda and the Milky Way are on a collision course, drawn together by gravity, closing the gap at about 70 miles per second. In about 4 billion years, the two galaxies will merge, their stars scattering and reforming into a single enormous elliptical galaxy that astronomers have already nicknamed Milkomeda. No stars will actually collide. The space between stars is so vast that two galaxies can pass through each other like ghosts, their stars threading past one another with room to spare. But the gravitational chaos will scramble everything. Our sun, if it is still around, will be flung into a new orbit. The night sky will be unrecognizable, and none of that matters to anyone alive today because it is happening on a timescale so long that human civilization, in its current form, will not be around to see it. Andromeda is not alone. It is part of a collection of galaxies called the Local Group, a gravitationally bound cluster that includes the Milky Way, Andromeda, the Triangulum Galaxy, and about 80 smaller dwarf galaxies scattered around them. Triangulum, also called M33, is the third largest member of the group. It sits about 3 million light-years from us, slightly farther than Andromeda, and contains perhaps 40 billion stars. The rest of the Local Group is made up of runts, dwarf galaxies with names like the Large Magellanic Cloud, the Small Magellanic Cloud, Sculptor, Fornax, and dozens of others, each containing anywhere from a few million to a few billion stars. Some orbit the Milky Way like moons. Others drift between the larger galaxies, tugged gently by gravity but not captured. The entire local group spans about 10 million light-years across. That is the size of our immediate cosmic neighborhood. Not the street you live on, not even the city, the neighborhood. And within that 10 million light-year bubble, there are only 3 galaxies large enough to matter in the grand census of stars. Everything else is a footnote. The local group is not special. It is not unique. It is simply the patch of the universe close enough for us to study in detail, the one cluster where we can resolve individual stars and measure distances with something approaching confidence. There are thousands of other groups like it, scattered across the cosmos, each one a small island of galaxies held together by gravity, drifting slowly through an ocean of empty space. The thing that makes the local group worth talking about is not what it contains. It is what it tells you about the structure of the universe. Galaxies do not float randomly, they clump together. Gravity pulls them into pairs, groups, clusters and superclusters, building a cosmic web of matter stretched across billions of light-years. And between those threads, there is nothing, not empty space in the casual sense, not vacuum, nothing, no galaxies, no stars, no light. Just vast stretches of darkness where the universe forgot to put anything at all. Stand on Earth, and you are standing on a planet orbiting a star in the outer arm of a spiral galaxy that is falling slowly toward a neighboring galaxy inside a small cluster of about 80 galaxies that is itself just one tiny knot in a web of structure spanning the observable universe. That is your address. That is where you are. And the first leg of that address, the jump from the Milky Way to Andromeda, is already 2.5 million light-years long. The second leg, from the local group to the next major galaxy cluster, is 10 times farther. And it only gets worse from there. The distances stop making sense. The numbers stop meaning anything. You can write them down, you can say them out loud, but your brain will not process them, not really. Because you are a creature built to navigate distances measured in footsteps, in miles, in hours of travel. You were not built for this. No one was. And yet here we are, trying to map it anyway, trying to measure the gaps between islands of light in an ocean that has no shore. The local group is small. It is a quiet corner of the universe, a handful of galaxies doing what galaxies do, spinning slowly, making stars, occasionally eating each other. If the universe were a city, the local group would be a single apartment building on the outskirts, barely visible from downtown. And from here, we are about to step outside and realize just how far the city actually stretches. The map of the universe does not begin with the local group, but it is the last place where the numbers still fit inside a human imagination. Past this point, the scale breaks. The distances become so large that light itself, the fastest thing in existence, starts to feel slow. And the space between the galaxies, the empty stretches we have been politely ignoring, becomes the dominant feature of the cosmos, not the galaxies, the nothing between them. The local group is not the universe. It is barely a whisper of it, a tiny cluster of galaxies huddled together in one corner of something so large that the human brain has no furniture to store it in. If you want to understand what the universe actually looks like, you need to step back, way back. So far back that the Milky Way shrinks to a point of light, then vanishes entirely, swallowed by the sheer scale of everything else. And when you do that, when you pull the camera back far enough to see the whole stage, what you find is not a random scattering of stars. What you find is structure, patterns, a vast web of galaxies stretching across billions of light years, clustered along filaments of dark matter, separated by voids so empty they make interstellar space look crowded. The universe, it turns out, has a shape. And mapping that shape has taken the better part of a century, thousands of astronomers, and some of the most powerful telescopes ever built. What they found was both more and less than anyone expected. Let's start with the boundary, the observable universe. That phrase gets thrown around a lot, usually without much explanation, and the result is that most people think it means the entire universe. It does not. The observable universe is the part we can see, the part where light has had enough time since the Big Bang to travel across space and reach our telescopes. The universe is 13.8 billion years old. Light moves fast, but it does not move infinitely fast. That means there is a horizon, a limit beyond which light simply has not had time to get here yet. The radius of the observable universe, measured from Earth, is about 13.8 billion light-years. Not because the universe stops there, but because the light from anything farther away has not arrived yet. It is still in transit, crossing a gap so large that even moving at 186,000 miles per second, it has not finished the trip. And here is the part that breaks people's brains. The universe has been expanding the entire time that light was traveling. So the objects we see at the edge of the observable universe, the galaxies whose light has been traveling for 13.8 billion years, are not 13.8 billion light-years away anymore. They are farther, much farther. Current estimates, accounting for the expansion of space itself, put the actual distance to the edge of the observable universe at about 46 billion light-years. The light we see tonight left those galaxies when they were much closer. But in the time it took that light to reach us, space stretched. The galaxies moved farther away, and the photons we are detecting are fossils, evidence of a universe that no longer exists in the form we are seeing. The observable universe is not the entire universe. That is worth repeating because it is one of the most commonly misunderstood ideas in cosmology. The universe beyond our horizon could be infinite. It could extend forever in all directions, filled with galaxies we will never see, stars that will never register on any instrument we build, because the light from them will never reach us. Or the universe could be finite, curved back on itself in some higher dimensional shape we cannot visualize. We do not know. We cannot know. What we can see is a sphere 46 billion light-years in radius, centered on us, filled with everything that has had time to send light in our direction. That sphere is the observable universe. That is the map we are trying to draw. For most of the 20th century, astronomers did not know how many galaxies were in that sphere. They knew there were a lot. Edwin Hubble's work in the 1920s had proven that the universe extended far beyond the Milky Way, that the faint smudges scattered across the sky were not clouds of gas but entire galaxies, each one containing billions of stars. But counting them was another problem entirely. Early telescopes could only see the brightest galaxies, the ones close enough or large enough to stand out against the darkness. Extrapolating from that sample to the entire universe was like trying to estimate the population of a city by standing on one street corner and counting the people who walked past in an hour. You would get a number, sure, but it would not mean much. The first serious attempt at a cosmic census came in the mid-1990s with the Hubble Deep Field. Astronomers pointed the Hubble Space Telescope at a tiny patch of sky in the constellation Ursa Major, a region so small it would take about 75 of them to cover the area of the full moon. They expected to see a handful of faint galaxies, maybe a few dozen. The exposure ran for 10 days. When the image came back, it contained about 3,000 galaxies. 3,000 in a patch of sky the size of a grain of sand held at arm's length. Every single one of those galaxies was invisible to the naked eye. Most of them had never been observed before. Some of them were so far away that their light had been traveling for more than 13 billion years, meaning we were seeing them as they existed when the universe was less than 1 billion years old. The image did not just expand the known galaxy count, it rewrote the entire sense of scale. Astronomers did the math. If a patch of sky that small contained 3,000 galaxies, and you tiled the entire sky with patches like that, you would end up with somewhere between 100 and 200 billion galaxies in the observable universe. That number held for about 2 decades. It showed up in textbooks, in planetarium shows, in every general audience explanation of cosmology. 100 billion galaxies, maybe 200 billion if you were being generous. It was a big number, but it was manageable. You could say it out loud without feeling ridiculous. Then, in 2016, a team led by Christopher Consolois at the University of Nottingham published a new analysis. They took the Hubble Deep Field data, combined it with observations from other deep sky surveys, and built a statistical model that accounted for galaxies too faint or too far away to detect directly. The model predicted that the earlier estimates were off, not by a little, by a factor of 10. The revised count came in at about 2 trillion galaxies, not 200 billion, 2 trillion. Let that sit for a second. 2 trillion galaxies, if you wanted to count them 1 per second, never stopping, never sleeping, it would take you 62,000 years. That is longer than human civilization has existed in any form we would recognize. Longer than agriculture, longer than writing, longer than cities. You would start counting before the pyramids were built, and you would still be counting today, and you would not even be halfway done. Every single one of those galaxies contains billions of stars. Some contain hundreds of billions. A few, like the largest ellipticals, contain trillions. Multiply it out, and you get a number so large it stops meaning anything. 10 to the 24th stars, maybe more. A 1 followed by 24 zeros. There are about 7 billion people on Earth. If you divided up all the stars in the observable universe evenly, every human being alive today would get about 100 billion galaxies, not stars, galaxies. You could give every person on Earth their own Milky Way 100 billion times over and still have leftovers. The 2 trillion figure is not exact. It is an estimate built on layers of assumption and extrapolation, but it is the best estimate we have, and even that number might be too low. A 2022 analysis published in Big Think argued that the true count could be closer to 6 trillion, maybe as high as 20 trillion, if you include all the faint dwarf galaxies that current telescopes cannot resolve. Those galaxies exist. We know they exist because we see them in the local group. Dozens of tiny satellite galaxies orbiting the Milky Way and Andromeda, each one containing only a few million stars. Scale that up across the entire observable universe and the count explodes, but we cannot confirm it. We can only model it, so 2 trillion is the number that stuck. Conservative, defensible, and still utterly incomprehensible. How do astronomers actually count galaxies? They do not sit at a telescope and tick them off one by one. That would take longer than the age of the universe. Instead, they use a technique called statistical extrapolation. You observe a small representative sample of the sky in as much detail as possible, count everything in that sample, and then multiply up to cover the whole sky. The Hubble Deep Field was one such sample. So was the Hubble Ultra Deep Field, an even longer exposure taken in 2004 that pushed deeper into space and revealed galaxies even farther away. The James Webb Space Telescope has continued that work, peering into the infrared where the most distant galaxies show up, their light stretched by the expansion of the universe into wavelengths that Hubble could not see. Each new deep field adds data points. Each new survey refines the model. And every time, the number goes up. The galaxies themselves are not all the same. They come in 3 basic types: shapes that repeat across the universe with surprising consistency. Spiral galaxies, like the Milky Way and Andromeda, have flat rotating disks with arms that curl outward from a central bulge. They are young, active, still making stars in their outer regions where clouds of gas and dust collapse under gravity. Elliptical galaxies are older, smoother, shaped like footballs or eggs. They contain mostly old stars and very little gas. Star formation in ellipticals has mostly shut down. They are retirement homes for stars, places where the fireworks have already happened and all that is left is the slow fade. Irregular galaxies are everything else, messy, asymmetric, often the result of collisions or gravitational disturbances. The Large Magellanic Cloud, one of the Milky Way's satellite galaxies, is an irregular. So is the result of most galaxy mergers, at least for the first few 100 million years before gravity smooths things out. Spirals are the most photogenic. They show up in posters and documentaries because they look like something a human brain can pass. Arms, a center, a structure that makes sense. But spirals are not the majority. Most galaxies in the universe are ellipticals or small irregulars. And the farther back in time you look, the stranger things get. The early universe, the first billion years after the Big Bang, was a chaotic place. Galaxies were smaller, more irregular, more prone to collisions. The smooth spiral structure we see in galaxies today took time to develop. It required billions of years of relatively undisturbed rotation, with gas settling into a disk and stars forming in orderly waves. In the early universe, that had not happened yet. The galaxies we see in the deepest Hubble and Webb images look messy, clumpy, more like rough drafts than finished products. They are galaxies in the process of becoming, caught at a moment when the rules had not fully settled. Some of those early galaxies are shockingly bright, brighter than they should be for their size and age. That brightness is one of the puzzles the James Webb Space Telescope was built to solve. When light from a distant galaxy reaches us, it has been traveling for billions of years. The farther away the galaxy, the further back in time we are seeing it. The most distant galaxies observed by Webb are seen as they existed only a few 100 million years after the Big Bang, in an era astronomers call the Cosmic Dark Ages. That name is a bit misleading. The universe was not literally dark, but it was darker than it is now. The first stars had only just begun to light up. The first galaxies were still forming, and the space between them was filled with neutral hydrogen gas that absorbed most wavelengths of light. The universe in its infancy was opaque, a foggy place where light could not travel far without being scattered or absorbed. Over time, the ultraviolet radiation from the first stars ionized that hydrogen, clearing the fog and allowing light to travel freely. That process, called reionization, took about 1 billion years. By the time it was over, the universe looked more or less like it does today, at least in terms of transparency. The galaxies Webb is observing now are sitting right at the edge of that transition, half in the fog and half out of it. Their light has been stretched so much by the expansion of the universe that what started as ultraviolet radiation has shifted all the way into the infrared. Hubble could not see it, Webb can. Every deep field image is a time machine. When you look at a galaxy 13 billion light-years away, you are not seeing it as it is now. You are seeing it as it was 13 billion years ago. The stars in that galaxy have aged. Some have died. The galaxy itself may have merged with others, changing shape entirely. Or it may have drifted so far away due to the expansion of space that it is no longer part of the observable universe. The light reaching your telescope tonight is the only evidence that galaxy ever existed in that form. It is a postcard from the past, and the past is the only version of that galaxy you will ever see. That is true for every object in the night sky. The farther away it is, the further back in time you are looking. The Sun as it was 8 minutes ago. Proxima Centauri as it was 4 years ago. Andromeda as it was 2.5 million years ago. A galaxy near the edge of the observable universe as it was when the universe itself was still an infant. You are not looking at the universe. You are looking at the history of the universe, layered across distance like rings in a tree. The map astronomers have built from all this data is not a simple one. It is not a flat catalogue of dots on a grid. It is a three-dimensional web, a structure that emerges when you plot the positions of millions of galaxies and step back to see the pattern. Galaxies are not scattered randomly. They cluster. They form groups, like the local group. Those groups collect into clusters, structures containing hundreds or thousands of galaxies bound together by gravity. Those clusters line up along filaments, vast threads of dark matter and ordinary matter stretching across hundreds of millions of light years. And between those filaments, there is almost nothing, just empty space, regions so devoid of galaxies that astronomers call them voids. The universe, when you map it at the largest scale, looks like a sponge or a web or the foam on top of a latte. Matter clings to the edges. The interior is hollow. The largest structures in the universe are these filaments and the voids between them. The Sloan Great Wall, a supercluster of galaxies discovered in 2003, stretches about 1.3 billion light-years across. The Hercules Corona Borealis Great Wall, identified in 2013, is even larger, spanning roughly 10 billion light-years. Structures that size should not exist, at least not according to the standard model of cosmology, which predicts that the universe should be roughly uniform at the largest scales. And it is, mostly. But there are wrinkles, lumps, places where gravity pulled matter together more aggressively than the average. Those lumps are where the galaxies are. The smooth parts are the voids, and the voids are everywhere. If you could somehow stand outside the observable universe and look at it from a distance, you would not see a cloud of galaxies. You would see a network. Bright threads of light connected by dim bridges, surrounding vast dark regions where almost nothing glows. The threads are the filaments, the dark regions are the voids, and the ratio between them is lopsided. By volume, the universe is mostly empty, not mostly as in 51%, mostly as in 80% or more. The galaxies, all 2 trillion of them, are crammed into the remaining 20%, clustered along the edges of the voids like cities along a coastline. The rest is absence, not space waiting to be filled, just space. Empty, expanding, and in no hurry to change. 2 trillion galaxies sounds like a lot. It is a lot, but when you spread them across a sphere 92 billion light-years wide, they start to look sparse. The average distance between galaxies is a few million light-years. In the densest regions, galaxy clusters, that distance shrinks. In the voids, it stretches, but even in the crowded regions, space dominates. If you shrank the Milky Way down to the size of a coin and placed it on a table, Andromeda would be another coin, sitting about 10 feet away. The next large galaxy, several more feet beyond that, and the table would stretch in all directions farther than you could walk in a day. That is the map. That is the grand tapestry. Islands of light floating in an ocean of nothing, held together by gravity, slowly drifting apart as space itself expands. The universe is not crowded. It is breathtakingly, incomprehensibly empty, and every telescope we point at the sky confirms it. The 2 trillion galaxies are real. We have the images, we have the data, but the images only show you the light. They do not show you the distance between the light sources. They do not show you the years it takes for a signal to cross from one galaxy to the next. They compress the universe into a flat picture, and the picture lies. It makes the cosmos look accessible, like a place you could visit if you had a fast enough ship. You cannot. The distances are too large. The expansion is too fast. Most of the galaxies we see tonight are already unreachable, even in principle, even if you could travel at the speed of light. The space between us and them is growing faster than light can cross it. They are visible, but they are gone. And with every passing second, more galaxies slip over that horizon, their light redshifting into invisibility, their futures severed from ours by the simple fact of distance. The map we have built is a map of ghosts. Galaxies that were seen from a time and place that no longer connects to where they are now. That is the grand tapestry. Beautiful, yes. Precise, yes. And unreachable. But before we can talk about the emptiness, we need to talk about the ruler. Because none of this mapping, none of this counting, none of this structure makes sense unless you understand how astronomers measure distance in the first place. How do you know a galaxy is 10 billion light-years away and not 5? How do you measure something so far that light takes longer than human civilization to cross it? That question has an answer. Several answers, actually, and every one of them is stranger than you would expect. But before we can talk about the emptiness, we need to talk about the ruler. Because none of this mapping, none of this counting, none of this structure makes sense unless you understand how astronomers measure distance in the first place. How do you know a galaxy is 10 billion light-years away and not 5? How do you measure something so far that light takes longer than human civilization to cross it? That question has an answer, several answers actually, and every one of them is stranger than you would expect. The tool astronomers use to measure cosmic distance has a name that sounds like it describes time, a light-year. Most people hear that phrase and assume it means a year, a duration, 12 months, 365 days. It does not. A light year is not a measurement of time. It is a measurement of distance. Specifically, it is the distance that light travels in 1 year, moving at its constant speed through the vacuum of space. And that distance is absurdly, almost comically large. Light moves at about 186,000 miles per second, not per hour, per second. In the time it takes you to blink, light travels roughly 14,000 miles. In 1 second, a beam of light could circle the Earth's equator 7.5 times. Hold that speed steady for an entire year, never slowing, never stopping, and you cover about 5.88 trillion miles. That is 1 light year. Not 5.88 million, not billion, trillion. A 1 followed by 12 zeros, multiplied by roughly 6. If you wanted to write it out in full, you would need a number so long it would fill half a page. The International Astronomical Union, the organization responsible for standardizing definitions in astronomy, has nailed down the exact figure. 1 light year equals 9 trillion. 460 billion, 730 million, 472,580.8 kilometers. That level of precision is not useful for casual conversation, but it matters when you are building models of the universe and need every digit to line up. For practical purposes, astronomers round it, 5.88 trillion miles, 9.46 trillion kilometers, close enough. The error in rounding is smaller than the error in measuring the distances themselves, so nobody loses sleep over it. Why use light years at all? Why not stick with miles or kilometers, units that people already understand? Because miles and kilometers stop being useful the moment you leave the solar system. The distance to the nearest star, Proxima Centauri, is about 25 trillion miles. That number is technically accurate, but it does not communicate anything. Your brain sees trillion and it shuts down. There is no reference point, no intuition, no way to picture what 25 trillion of anything looks like. But if you say Proxima Centauri is 4.2 light-years away, the number suddenly has structure. You know how fast light moves. You know how long a year is. You can imagine, or at least try to imagine, what it means for light to travel for 4 straight years before arriving at a destination. The number has meaning, not comfortable meaning, but meaning. Light years are the first rung on a ladder that keeps climbing. The Milky Way is about 100,000 light-years across. Andromeda is 2.5 million light-years away. The edge of the observable universe sits roughly 46 billion light-years from Earth, and with every step up that ladder, the numbers get harder to hold in your head, but they stay manageable, barely. If astronomers used miles, the numbers would be so large they would require scientific notation just to write down, and at that point you have lost the audience. Light years keep the scale just inside the boundary of human comprehension, just barely. The speed of light is not arbitrary. It is the speed limit of the universe. Nothing with mass can move faster than light in a vacuum. Not a spacecraft, not a particle, not information. This is not a technological limit. It is not something engineers will figure out how to bypass with better engines or clever tricks. It is a rule written into the structure of space-time itself. Einstein proved it in 1905 with special relativity, and every experiment since then has confirmed it. As an object with mass accelerates closer and closer to the speed of light, it requires more and more energy to keep accelerating. By the time you reach 99% of light speed, the energy required to go faster has already become astronomical. At 99.9%, it climbs higher. At 99.99%, higher still. You can keep adding nines forever, pouring in more energy, and you will get closer and closer to light speed, but you will never reach it. The curve is asymptotic. Light speed is the horizon you can approach but never cross. Light itself moves at that speed because light has no mass. Photons, the particles that make up light, are massless. That is why they can move at the universal speed limit. Anything with mass cannot. And because light always moves at the same speed, it becomes the perfect ruler for measuring distance in a universe where everything else is moving, shifting, expanding, and refusing to sit still. The speed of light is constant. It does not change based on how fast you are moving or where you are in the universe. A photon emitted by a star 10 billion light-years away travels at the same speed as a photon emitted by a flashlight in your hand. That consistency is what makes light useful as a measuring stick. It is the one thing in the cosmos that does not lie. Here is where it gets strange. When you look at a star 10 light-years away, you are not seeing that star as it is right now. You are seeing it as it was 10 years ago. The light you are detecting tonight left that star a decade ago. It has been traveling through space ever since, moving at 186,000 miles per second, covering trillions of miles, until it finally reached your telescope. In the time that light was in transit, the star kept living. It kept burning hydrogen, kept spinning, kept doing whatever stars do. But you do not see any of that. You see the version of the star that existed when that particular batch of photons left its surface. The light is a postcard from the past, and the farther away the object is, the older the postcard. Look at the sun, and you are seeing it as it was 8 minutes ago. Look at Proxima Centauri, and you are seeing it as it was 4 years ago. Look at a galaxy 100 million light-years away, and you are seeing it as it existed 100 million years ago, during the age of dinosaurs on Earth. Look at a galaxy 10 billion light-years away, and you are seeing it as it was when the universe was less than 4 billion years old, long before the Sun or Earth or anything in our solar system had formed. Astronomers call this look-back time. Every observation is a time machine. The deeper you look into space, the further back in time you see. Distance and time are not separate in astronomy. They are the same thing, measured in the currency of light. NASA put it plainly: the farther an object is, the farther in the past we see it. That is not a metaphor. It is a direct consequence of the fact that light has a finite speed and the universe is very, very large. If a supernova explodes in a galaxy 100 light-years away, we will not see the explosion for 100 years. The star could already be gone, its remnants cooling into a neutron star or black hole, and we would not know. The light from the explosion is still on its way. For the next century, anyone looking at that star from Earth will see it as it was before the explosion, burning steadily, giving no hint of the violence about to unfold. Then one night, the light from the supernova will arrive. The star will suddenly brighten, flare, and fade. And astronomers will record the event as if it just happened, even though it happened a century ago. The past and the present collapse into the same observation. This is not a problem. It is a feature. Look-back time allows astronomers to study the history of the universe directly. You do not need to guess what galaxies looked like billions of years ago. You just point a telescope at a galaxy billions of light-years away and look. There it is, frozen in time, exactly as it was when the universe was young. The James Webb Space Telescope is built specifically to exploit this. By observing the most distant galaxies, the ones whose light has been traveling for more than 13 billion years, Webb is looking at the universe in its infancy. The galaxies it detects are not relics. They are live images, photons that left those galaxies when the cosmos was still figuring out how to make stars, captured in mid-flight and delivered to a mirror floating in space 1,000,000 miles from Earth. But there is a complication. The universe is not static. It is expanding. And that expansion changes everything. When astronomers say a galaxy is 10 billion light-years away, they mean the light from that galaxy has been traveling for 10 billion years. But the galaxy itself is not 10 billion light-years away anymore. It is farther, much farther. Because while the light was in transit, space itself stretched. The fabric of space-time, the underlying grid that everything sits on, has been expanding since the Big Bang. Galaxies are not flying through space. Space is carrying them apart, like dots on the surface of a balloon that is being inflated. The farther apart two galaxies are, the faster the space between them expands, and past a certain distance, that expansion happens faster than light can cross it. This is not a violation of the speed limit. Nothing is moving through space faster than light, but space itself is not bound by that rule. Space can expand as fast as it wants, and at the largest scales it does. The result is that the edge of the observable universe, the most distant objects we can see, are not 13.8 billion light-years away. They are closer to 46 billion light-years away, accounting for how much space has stretched since the light we are seeing left those objects. The photons have been traveling for 13.8 billion years, but the source has been receding the entire time. The distance has grown. By the time the light reaches us, the object is 3 times farther away than it was when the light started its journey. That expansion introduces a new wrinkle into the measurement problem. Distance in cosmology is not a single number. It is several numbers, depending on what you mean by distance. There is the light travel distance, the amount of time the light has been traveling. There is the comoving distance, the distance to the object right now, accounting for expansion. There is the angular diameter distance, which affects how large the object appears in the sky. And there is the luminosity distance, which affects how bright the object looks. All of these are different, and which one you use depends on the question you are asking. When astronomers say a galaxy is 10 billion light-years away, they usually mean the light travel distance. But the galaxy itself, at this exact moment, is much farther. And by the time you finish reading this sentence, it will be farther still. The cosmic horizon, the boundary of the observable universe, is not a wall. It is a limit on information. Light from beyond that horizon has not had time to reach us yet. The universe is 13.8 billion years old. Light can only travel 13.8 billion light years in that time, adjusted for expansion. So there is a sphere around Earth, centered on us, beyond which no light has arrived. That does not mean the universe ends there. It almost certainly does not. The universe beyond the horizon is probably filled with galaxies, stars, planets, maybe even other civilizations, but we cannot see them. We will never see them. The light from those regions has not reached us, and depending on how fast the universe is expanding, it may never reach us. Some of those galaxies are already unreachable, even in principle. The space between us and them is expanding faster than light can cross it. They are visible in the sense that they exist, but they are functionally gone, separated from us by a gap that will only grow wider with time. This is one of the loneliest ideas in cosmology. Most of the universe is not just far away, it is inaccessible. You could build a ship that travels at the speed of light, point it at one of those distant galaxies, and set off on a journey that lasts billions of years, and you would never arrive. The galaxy would recede faster than you could chase it. The gap would widen. You would spend eternity falling behind, watching your destination drift farther into the distance, until eventually it redshifted out of existence entirely, its light stretched into wavelengths so long that no instrument could detect it. You would be alone in the dark, surrounded by nothing, with no way forward and no way back. The expansion of space does not care about your ambitions. It does not care about faster engines or better fuel. It is a one-way door, and once something crosses the threshold, it is gone. Light years are the currency of that separation. Every time you add a zero to the distance, you are not just making the number bigger, you are adding time, adding history, adding a gap that cannot be closed. A galaxy 1 billion light years away is not just far, it is 1 billion years in the past. A galaxy 10 billion light years away is 10 billion years in the past. You are not looking at a map of where things are. You are looking at a timeline of where things were, layered across space like frames in a film. The universe does not have a present tense. It only has a past, delivered one photon at a time, sorted by distance into a history that plays out across the sky. And the deeper you look, the stranger that history gets. The galaxies at the edge of the observable universe are not just distant, they are young, primitive, messy. They are galaxies in the process of forming, caught at a moment when the rules were still being written. The light reaching us tonight from those galaxies left when the universe was less than 1 billion years old. The stars in those galaxies have been dead for more than 10 billion years. The galaxies themselves have merged, evolved, changed shape entirely. What we see is a snapshot of something that no longer exists in that form, a fossil made of light. And every observation we make with Webb or Hubble or any other telescope is just adding more fossils to the collection. We are not exploring the universe, we are excavating it. The light year is the ruler that makes that excavation possible. It is the only unit that works at this scale, the only way to translate the raw data of redshift and luminosity into something resembling a distance. But it comes with baggage. Every light year you measure is also a year you lose. A year the object has spent drifting farther away, changing, aging, becoming something you will never see. The light year is not just a distance, it is a reminder that the universe is not waiting for you. It is expanding, moving, pulling everything apart at a rate that increases with distance. The farther you look, the faster things recede. And at some point, far enough out, they recede faster than light can follow. That is the edge, not a wall, not a boundary, just a horizon where the math stops working and the light stops arriving. Beyond that line, the universe continues. We just do not get to see it. So when astronomers say a galaxy is 2 billion light-years away, what they mean is this: the light you are seeing left that galaxy 2 billion years ago. The galaxy at this exact moment is farther than that, maybe 3 or 4 billion light-years away, depending on how fast space has been expanding in the interim. You are seeing a version of that galaxy that no longer exists. The stars you are looking at have aged. Some have died. The galaxy may have collided with another galaxy, merging into something new, or it may have drifted so far that it is no longer part of the observable universe, its light stretched into wavelengths no telescope can detect. The distance is not a fixed thing. It is a moving target, a number that changes every second as space expands and galaxies drift farther apart. And the only thing anchoring that number is the speed of light, 186,000 miles per second. Constant, unchanging, the one reliable fact in a universe that refuses to sit still. Light is fast. Bill Nye said it plainly. Nothing travels faster than light. That is the rule. That is the speed limit. And because of that limit, distance in the universe is also a measure of time. The farther something is, the older its light. The older the light, the further back in time you are looking. And at the largest distances, the farthest edges of the observable universe, you are looking all the way back to the beginning, to a time when galaxies were just forming, when stars were just igniting, when the universe itself was still a child. The light year is the tool that lets you do that. It is the bridge between distance and time, the conversion factor that turns space into history. And every time you use it, every time you say a galaxy is 10 billion light-years away, you are also saying that galaxy is 10 billion years in the past. Distance and time are the same thing, measured in the only currency the universe accepts: light. Moving at one speed, forever, carrying information from the past into the present, one photon at a time. That is the light-year ledger. That is the ruler astronomers use to measure the immeasurable. And it works, mostly. It gives you distances, ages, a sense of scale. But it also gives you something else, a sense of loss. Because every measurement is also a separation. Every light year is another year the object has spent drifting away. And the farther you measure, the wider the gap becomes, until eventually you reach the edge, the cosmic horizon. The place where the light stops arriving and the universe beyond continues without you. The light year measures distance, yes, but it also measures absence, the space between things, the time it takes for information to cross a gap so large that by the time it arrives, the source is already gone. And that absence, that space, that gap between the light sources is what we need to talk about next. Because the universe is not just large, it is mostly empty. And the empty parts, the voids, the stretches of space where no galaxies shine, are not just background, they are the dominant feature. 2 trillion galaxies sounds like a lot. But when you measure the space between them, when you add up the volume of the voids, you realize something uncomfortable. The universe is not a collection of galaxies separated by space. It is a collection of voids, with galaxies clinging to the edges, and the voids are everywhere. When astronomers first started mapping the large-scale structure of the universe, they expected to find galaxies scattered more or less evenly across space. A random distribution, maybe with some clustering here and there, but nothing too dramatic. That is not what they found. What they found instead was a pattern so striking, so unexpected, that it forced a complete rethinking of how the cosmos is organized. Galaxies are not scattered randomly, they are arranged in a web. a vast three-dimensional network of filaments and walls surrounding enormous empty regions that contain almost nothing at all. The technical term for this structure is the cosmic web, and once you see it, you cannot unsee it. The universe has architecture, and most of that architecture is absence. The cosmic web showed up clearly for the first time in the 1980s, when astronomers began conducting large-scale redshift surveys. A redshift survey is exactly what it sounds like. You point a telescope at a patch of sky, measure the redshift of every galaxy you can detect, and use that redshift to calculate distance. Do that for thousands of galaxies, plot their positions in 3 dimensions, and a structure emerges. The first major survey was called the CFA Redshift Survey, led by a team at the Harvard-Smithsonian Center for Astrophysics. When they published their results, the astronomy community stared at the data for a long time, trying to figure out what they were looking at. The galaxies were not spread evenly. They were clustered along thin strands, forming walls and filaments that stretched across hundreds of millions of light years. And between those strands, there were gaps, huge gaps, regions where almost no galaxies appeared at all. One of those gaps became famous almost immediately, the Bootes Void, discovered in 1981 by Robert Kirshner and his colleagues, is a roughly spherical region of space about 330 million light-years across. It sits in the direction of the constellation Bootes, which is where the name comes from. Inside that volume, a region large enough to contain thousands of galaxies, there are only about 60 galaxies, 60, in a space where you would expect to find 10,000. The void is not completely empty, but it is so underdense, so dramatically lacking in galaxies compared to the surrounding regions, that it might as well be. If you were somehow standing inside the Bootes Void, the night sky would look almost black. A handful of faint smudges scattered across the darkness, and nothing else. No Milky Way, no neighboring galaxies. Just an empty sky and the uncomfortable realization that you are in the middle of nowhere, with the nearest significant structure hundreds of millions of light-years away in every direction. The Bootes Void is not unique. It is just one of the first voids astronomers identified clearly enough to measure. Since then, hundreds of others have been mapped. The largest known void, discovered in 2004, is called the Giant Void. It sits roughly 1 billion light-years away in the direction of the constellation Eridanus and spans about 1 billion light-years across. 1 billion light-years. To put that in perspective, the distance from the Milky Way to Andromeda is about 2.5 million light-years. The Giant Void is 400 times wider than that. If you shrank the entire local group down to the size of a quarter and placed it at one edge of the Giant Void, the opposite edge would be 100 feet away, and the space in between would contain almost nothing. A few scattered dwarf galaxies, maybe some isolated stars or clouds of gas, but for the most part, just emptiness, cold, dark, and expanding. Voids are not anomalies. They are not rare pockets of emptiness surrounded by dense regions. They are the default, the large-scale structure of the universe. When you map it at the largest scales, consists primarily of voids. The galaxies, the 2 trillion galaxies that make up the observable universe, are not spread throughout that volume. They are concentrated in the spaces between the voids. Along filaments, thin threads of matter where gravity has pulled galaxies together into long chains stretching across hundreds of millions of light-years. Along walls, flat sheets of galaxies forming the boundaries between voids. And at the intersections of those filaments, in dense clusters where thousands of galaxies crowd together in a relatively small region of space. The voids themselves are the interior, the hollow spaces surrounded by the web, and they take up most of the room. Think of it like a sponge. If you zoom in close on a kitchen sponge, you see tiny strands of material forming a network. The strands are where the substance is. The holes, the open spaces between the strands, are what give the sponge its structure. The universe is the same way. The galaxies are the strands. The voids are the holes, and the holes are bigger than the strands, much bigger. When you add up the volume of all the voids in the observable universe and compare it to the volume occupied by galaxies, filaments, and clusters, the ratio is lopsided. The voids win by a lot. Estimates vary depending on how you define a void and what density threshold you use, but the general consensus is that voids occupy somewhere between 60 and 80% of the total volume of the universe. 60 to 80%. That means the galaxies, all 2 trillion of them, are crammed into the remaining 20 to 40%. The universe is not a sea of galaxies with a few empty patches. It is a sea of emptiness with a few crowded edges. How do voids form? Why does the universe arrange itself this way? The answer comes down to gravity and time. In the very early universe, matter was spread almost evenly across space. Almost, but not quite. There were tiny fluctuations in density, small random variations that showed up as ripples in the cosmic microwave background. Some regions had slightly more matter than average, others had slightly less. Those differences were minuscule, less than 1 part in 100,000, but they were enough. Gravity is patient. It does not care how small the difference is, it just pulls. Regions with slightly more matter had slightly stronger gravity, which pulled in more matter from the surrounding areas. The denser regions got denser, the less dense regions got less dense. Over hundreds of millions of years, that process continued. Matter flowed toward the densest points, collapsing into filaments and clusters, while the regions that started out slightly underdense became more and more empty as their matter drained away. The result is the cosmic web. Gravity built the filaments and clusters by pulling matter together. The voids are what was left behind. They are not empty because something removed the matter. They are empty because the matter was never there in large amounts to begin with, and what little was there got pulled away toward denser regions over billions of years. Voids are the architectural consequence of gravity acting on an almost uniform distribution of matter over cosmological timescales. They are the spaces between the places where stuff decided to collect, and they are growing. The universe is expanding, and that expansion affects voids more dramatically than it affects denser regions. Inside a galaxy cluster, gravity is strong enough to hold the galaxies together. The cluster is bound. The galaxies orbit each other, sometimes collide, but they stay together as a group. The expansion of space does not pull them apart because gravity is stronger than the expansion at that scale. Inside a void, there is not enough matter to generate that kind of gravitational binding. The expansion of space dominates, the void stretches. The few galaxies that do exist inside a void drift farther apart as space itself expands between them. Over time, voids get bigger and emptier. The filaments and clusters surrounding them stay relatively stable, held together by gravity, while the voids between them continue to inflate like balloons. There is an analogy that gets used a lot when describing this structure, and it works surprisingly well. Imagine a pot of boiling water with soap bubbles forming on the surface. The bubbles are the voids. The thin films of soap where the bubbles touch are the filaments and walls where galaxies cluster. The intersections where multiple bubbles meet are the galaxy clusters, dense knots of matter packed into small regions. The structure is foam. The universe, at its largest scale, looks like foam, bubbles of emptiness surrounded by thin skins of matter. The bubbles are the main feature. The soap is just what is left over. That analogy captures the visual structure, but it does not quite capture the scale. Soap bubbles are fragile, temporary, a few inches across. Cosmic voids are hundreds of millions of light-years wide and have been around for billions of years. They are not going to pop. They are not going to collapse. They are permanent features of the universe, carved out by gravity and inflation, and they will remain as long as the universe continues to expand. The voids are not temporary gaps waiting to be filled. They are part of the design. You would think that a region of space 300 million light-years across, with almost no galaxies, would be completely empty, just vacuum, pure nothingness. That is not quite true. Voids are underdense, not zero-dense. There is still matter inside them, just much less than you would find in a typical region of space. The few galaxies that do exist inside voids tend to be small, faint and isolated. Dwarf galaxies that never merged with anything larger, quietly burning through their gas and making stars at a slow, unremarkable pace. There might be stray clouds of intergalactic gas, hydrogen left over from the early universe that never collapsed into anything. There might be dark matter. In fact, there almost certainly is dark matter, because dark matter is everywhere, spread throughout the universe in concentrations that follow the same large-scale structure as ordinary matter. The voids have less dark matter than the filaments and clusters, but they are not devoid of it. Dark matter does not clump as tightly as ordinary matter because it does not interact with light or normal matter except through gravity. It forms a more diffuse web, and some of that web passes through the voids. But even accounting for the dark matter, the stray gas, and the handful of faint galaxies, voids are still overwhelmingly empty. If you were somehow teleported to the center of a void, far from any of the scattered dwarf galaxies that might be drifting around the edges, the experience would be one of profound isolation. The nearest galaxy could be tens of millions of light-years away. The nearest galaxy cluster, hundreds of millions. You would see almost nothing in any direction. A black sky, cold and silent, with no Milky Way, no nearby stars, no structure at all, just darkness. The light from distant galaxies would be so faint and so far away that even with a powerful telescope you would struggle to find them. You would be in the middle of the largest architectural feature in the universe, surrounded by more empty space than any human has ever imagined, with no way to reach anything and no reason to believe anything would ever reach you. There is something almost deliberate about the structure. The universe did not have to arrange itself this way. Gravity could have pulled matter into a more uniform distribution, clumping it into clusters scattered evenly across space with no large-scale voids. That is not what happened. Instead, the universe built a web, a network, a pattern that repeats at every scale, from superclusters of galaxies down to the smallest filaments, always the same basic structure, dense regions connected by threads surrounding voids. It is efficient in a way. Gravity had limited time and limited matter to work with, and it used both to build the largest structures it could manage before the expansion of space started pulling everything apart. The voids are not wasted space. They are the necessary consequence of that construction. You cannot build a web without holes. Christopher Consolis, the astronomer who led the 2016 study that revised the galaxy count to 2 trillion, put it plainly. We are missing the vast majority of galaxies because they are very faint and far away. That statement applies to the voids as much as anywhere else. The galaxies inside voids, the ones we have not detected yet, are not missing because they do not exist. They are missing because they are too faint, too far, and too isolated to show up in current surveys. Future telescopes with better sensitivity will find more of them. But even when they do, even when we map every faint dwarf galaxy hiding inside the voids will still be voids. The additional galaxies will not fill the space. They will just add a few more dots to an otherwise empty canvas. The structure will not change. The voids will remain the dominant feature. It boggles the mind. Consoli said in another interview that over 90% of the galaxies in the universe have yet to be studied. That is true for the voids as well. Most of the volume of the universe has barely been surveyed. We have mapped the filaments and clusters in reasonable detail because that is where the bright galaxies are, the ones we can see easily. But the voids, the vast empty regions that make up most of the cosmos, are still largely unexplored. We know they are there. We have measured their size. We can see the structure they create in the cosmic web. But we have not looked inside them carefully enough to catalogue what little might be there. The voids are the last frontier, not because they are difficult to reach, but because they are difficult to see. There is almost nothing there to observe. Mark Postman, another astronomer who has worked on deep-field galaxy surveys, made the same point. We simply don't see the light from 2 trillion galaxies. Some of that missing light is in the voids. Some of it is scattered throughout the universe, hidden in faint dwarf galaxies that current instruments cannot resolve. But the underlying problem is the same. The universe is bigger, emptier, and darker than our telescopes can fully capture. We are mapping shadows, inferring structure from the light that manages to reach us, and guessing at what fills the spaces in between. The voids are part of that guess. We know they exist, we can measure their boundaries, we can calculate their volume. But we cannot see inside them clearly enough to say with certainty what, if anything, is there. And there is one more wrinkle. The voids are not all the same size. Some are relatively small, only a few tens of millions of light years across. Others, like the giant void, are more than 1 billion light years wide. The size distribution follows a pattern. There are more small voids than large ones, which makes sense. Gravity had an easier time carving out small empty regions than large ones. But the largest voids, the ones that span a significant fraction of the observable universe, are harder to explain. They require very specific initial conditions, very particular arrangements of matter and dark matter in the early universe to form at all. The fact that they exist suggests that the early universe had structure on scales much larger than anyone expected. Tiny fluctuations in density that were spread across such vast distances that they could only have been imprinted during the first fractions of a second after the Big Bang, during the period of cosmic inflation when the universe expanded faster than light. The voids are fossils. Not fossils of matter, but fossils of structure. They are the preserved imprints of conditions that existed in the early universe, blown up to cosmic scale by billions of years of expansion and gravitational collapse. By mapping the voids, astronomers are mapping the initial state of the cosmos, reading the ripples that were there from the beginning and following them forward through time to see where they led. The voids are not empty space, they are information. Data encoded in the absence of galaxies, waiting to be decoded. The cosmic web is not a metaphor, it is a real physical structure, and the voids are its defining feature. Without the voids, the filaments and clusters would not exist. Without the empty regions pulling matter away from certain areas and concentrating it in others, the universe would look completely different. The galaxies would be spread more evenly. There would be no walls, no threads, no intersections where thousands of galaxies pile up in dense clusters. The voids carved out the space. Gravity filled in the edges, and the result is the universe we see tonight. A web of light surrounding oceans of darkness, stretching across 92 billion light years, most of it empty, most of it silent, most of it waiting in a state of absence that will last as long as the cosmos does. 2 trillion galaxies sounds like a lot until you measure the space they are not in. The voids are the architects of that absence. They are the reason the universe looks the way it does, and they are everywhere. Between every galaxy cluster, behind every filament, filling the gaps in the cosmic web, there are voids. quiet, cold, and growing larger with every passing second as the expansion of space pushes them farther apart. The universe is not crowded, it is hollow, and the hollow parts are winning. So when astronomers talk about mapping the universe, they are not just mapping where the galaxies are, they are mapping where the galaxies are not, the voids, the empty regions that make up the majority of the cosmos. And the more they map, the more they realize that the voids are not background. They are foreground, they are the structure. The galaxies are just decorations clinging to the edges, small bright islands in an ocean of nothing that stretches farther than any telescope will ever see. That ocean has a size, a volume, a percentage. And in the next part of this story, we are going to measure it. So we have the voids. We know they exist. We know they are enormous, that they span hundreds of millions of light years, that they contain almost no galaxies. We know the cosmic web surrounds them, that galaxies cluster along filaments and walls like cities clinging to a coastline. But knowing that voids exist and understanding what 80% empty actually means are two different things. Numbers like that do not land intuitively. 80% sounds like a lot, it is a lot, but your brain hears it and moves on. It does not stop to picture what 80% of the observable universe actually looks like when translated into physical space. So let's do that. Let's measure the emptiness. Let's quantify the nothing and see what we are actually dealing with. The first challenge is defining what we mean by empty. In everyday language, empty means nothing. A room is empty if there is no furniture in it. A tank is empty if there is no gas in it. The word implies absence, a total lack of the thing you were expecting to find. The universe does not work that way. Space is never completely empty in the absolute sense. Even the darkest, coldest, most isolated regions of the cosmos contain something, a stray hydrogen atom drifting through the void. A photon left over from the cosmic microwave background, stretched into a radio wavelength so long it would take a detector the size of a planet to register it. A wisp of dark matter passing through, invisible and undetectable except through its gravitational influence on things millions of light years away. Empty in cosmology does not mean zero. It means almost zero, and the difference between almost zero and actually zero is where things get interesting. Cosmologists measure emptiness using a concept called density contrast. The idea is simple. You start with the average density of matter in the universe, not just ordinary matter, the stuff that makes up stars and planets and gas clouds, but all matter, including dark matter. Current estimates put the average density of the universe at about 1 proton per 4 cubic meters. 1 proton per 4 cubic meters. That is the baseline. That is what counts as average in the cosmos. If you were standing in a region of space that had exactly that density, you would be standing in a perfectly average part of the universe. Not dense, not empty, just average. Most of the matter would be dark matter, invisible and intangible, with only a tiny fraction showing up as normal atoms. But the total mass, averaged over a large enough volume, would match the cosmic mean. Now take that number and compare it to the density inside a void. Inside a typical void, the density is not 1 proton per 4 cubic meters. It is closer to 1 proton per 40 cubic meters. Or 1 per 400, or in the largest, emptiest voids, 1 per several thousand. The exact number varies depending on which void you are measuring and how far from the edges you go, but the pattern is consistent. Voids are underdense by a factor of 10, 100, sometimes more. They are not just a little emptier than average, they are dramatically, overwhelmingly emptier. If the average density of the universe is already so low that it barely registers as anything, The density inside a void is low enough that calling it nothing starts to feel justified. That factor of 10 or more is the density contrast. It is the ratio between the density in a void and the density in the surrounding filaments and clusters. The filaments, where galaxies actually live, are overdense. They contain more matter than average, sometimes 10 times more, sometimes 100 times more in the densest galaxy clusters. The voids are underdense by the same factor in the opposite direction. The contrast between the two is what gives the cosmic web its structure. Matter piles up in some places and drains away from others, and the result is a universe where most of the volume contains almost nothing, while a small fraction of the volume contains almost everything. Here is where the 80% figure comes from. When astronomers map the large-scale structure of the universe, they are not just identifying where galaxies are, they are measuring the density of matter throughout space, using galaxy surveys, gravitational lensing, and observations of the cosmic microwave background to build a three-dimensional map of how mass is distributed. They divide space into regions based on density. High-density regions are filaments and clusters. Low-density regions are voids. The boundary between the two is somewhat arbitrary, a threshold you pick based on what you are trying to measure, but the general pattern holds no matter where you draw the line. When you add up the volume of all the regions that fall below a certain density threshold, regions where the matter density is significantly lower than the cosmic average, you get a number somewhere between 60 and 80% of the total volume of the observable universe. Most estimates land closer to 80. That is not a guess. That is a measurement derived from decades of survey data and cross-checked against computer simulations of how structure forms in an expanding universe. 80% of the volume of the universe is underdense, 80% is voids. That does not mean 80% is completely devoid of matter. It means 80% contains far less matter than you would expect if the universe were uniform. The remaining 20%, the filaments and clusters, contains most of the galaxies, most of the stars, most of the gas, and most of the ordinary matter that makes up everything we can see. The mass distribution is inverted compared to the volume distribution. Voids occupy 80% of the space, but contain less than 10% of the mass. The filaments and clusters occupy 20% of the space, but contain more than 90% of the mass. The universe is lopsided, profoundly structurally lopsided. And that lopsidedness is not an accident. It is the result of gravity acting on an almost uniform distribution of matter over billions of years. Let's put that in perspective. Imagine you have a room the size of a football stadium. You fill it with sand, spreading the grains evenly across the floor until the entire surface is covered in a thin, uniform layer. Then you turn on a fan, a very patient fan. The fan blows gently, consistently, for years, decades, centuries. The sand starts to drift. Grains pile up in some areas where the airflow converges. Other areas lose grains as the wind carries them away. Over time, the sand collects into drifts and ridges, leaving large patches of bare floor in between. When you step back and look at the stadium, you see that most of the floor is empty. The sand is still there, all of it, but it is concentrated in a small fraction of the total area. The empty patches are not empty because someone removed the sand. They are empty because the sand drifted away, pulled toward the places where it was already starting to pile up. That is the universe. The sand is matter. The fan is gravity. The empty floor is the voids. And the drifts and ridges are the filaments and clusters where galaxies form. The analogy breaks down in one important way. Sand is visible. You can see where it piled up and where it did not. In the universe, most of the matter is dark matter, which does not emit light and cannot be seen directly. You can only infer where it is by watching how it bends light from background galaxies, or by measuring how it influences the motion of visible matter. The cosmic web is mostly invisible. What we see when we look at the universe, the galaxies and stars and glowing gas, is just the ordinary matter, the small fraction of the total mass that happens to interact with light. The dark matter, which makes up about 85% of all matter, forms its own web, a shadow structure that the galaxies trace but do not fully reveal. The voids are underdense in dark matter too, not just in ordinary matter. That makes them even emptier than they appear. If you could somehow see dark matter, if you could map its distribution directly, the voids would still be voids, darker, quieter, more profoundly empty than the maps of galaxy positions suggest. What does 80% empty actually look like on the ground? Imagine you are standing on a planet in a galaxy that somehow ended up inside a void, not near the edge, where you might still see a few neighboring galaxies in the distance. Deep inside, as far from the filaments as you can get, you look up at the night sky. What do you see? Almost nothing. The nearest galaxy could be 50 million light-years away. The nearest large galaxy, 100 million. At those distances, even the brightest galaxies are too faint to see with the naked eye. You would need a telescope, a good one, and even then, the sky would look sparse. A handful of dim smudges scattered across the darkness, each one representing a galaxy containing billions of stars, but so far away and so faint that it barely registers. There would be no Milky Way stretching across the sky, no Andromeda, no local group. Just a few isolated points of light, separated by vast stretches of black. You would feel the isolation immediately, not physically. You would not notice anything different about the space around you. The planet would spin normally, the gravity would feel the same. The air, if there was air, would behave exactly as it does on Earth, but the sky would tell you everything. You are alone, not just far from home, alone in a way that has no analogy in human experience. The nearest significant structure, the nearest place where galaxies cluster together in numbers large enough to form a recognizable cosmic neighborhood, is hundreds of millions of light-years away. Light from that structure, traveling at 186,000 miles per second, would take hundreds of millions of years to reach you. If you sent a signal, a radio transmission, a burst of light, anything, it would travel outward into the void at the speed of light, and it would not reach the nearest galaxy cluster for longer than complex life has existed on Earth. You would be stranded in a bubble of emptiness so large that escape is not just impractical, it is impossible. The void is not a place you visit, it is a place you are trapped in, and the voids are growing. The expansion of space affects underdense regions more than dense regions because there is less matter to hold things together. In a galaxy cluster, gravity is strong enough to keep the galaxies bound. The cluster stays together, orbiting a common center of mass, even as the universe expands around it. In a void, there is not enough matter to generate that kind of binding. The expansion dominates. The void stretches. The few galaxies that do exist inside a void drift farther apart as the space between them grows. Over billions of years, voids get larger and emptier. The filaments surrounding them stay relatively stable, held together by gravity, while the interior regions inflate. The universe is not just mostly empty, it is becoming more empty over time. Here is the uncomfortable part. The voids are not background. They are not the space left over after you account for the galaxies. They are the primary structure. When you map the universe at the largest scales, what you see is not a collection of galaxies with gaps in between. What you see is a collection of voids with thin shells of galaxies coating their surfaces. The cosmic web is the skin, the voids are the body, and the skin is thin, very thin. If you measured the thickness of a typical filament, the width of the region where galaxies actually cluster, and compared it to the diameter of the voids that filament surrounds, the ratio would be absurd. The filaments are a few tens of millions of light years thick. The voids they surround can be hundreds of millions of light years across. The shell is a tiny fraction of the volume. The interior is everything else. Think of a soap bubble again. The film of soap is where the matter is. The air inside the bubble is the void. The film is thin, a few molecules thick, stretched across a volume thousands of times larger. Pop the bubble, and the film collapses into almost nothing. The air it was holding, the volume it defined, vanishes. The universe is the same structure, but it does not pop. The bubbles are permanent. The voids are stable. They have been here for billions of years, and they will remain for billions more, growing larger as the universe expands, their interiors becoming emptier as the few galaxies inside them drift farther apart. The cosmic web is not a temporary phase. It is the final structure, the shape the universe settled into after gravity finished pulling matter together into the densest configurations it could manage. The voids are what was left behind, and they are winning. So what does it mean to say the universe is 80% empty? It means that if you picked a random point in space, anywhere in the observable universe, there is an 80% chance you would land inside a void, not near a galaxy, not in a star-forming region, not in a cluster or a filament, inside a void. Surrounded by darkness, with the nearest galaxy millions or tens of millions of light years away, and no reasonable prospect of ever reaching it. The odds are stacked overwhelmingly in favor of emptiness. The galaxies, the stars, the planets, the places where complexity and structure and life can exist, are statistical outliers, rare pockets of density in an ocean of nothing. If the universe were a lottery, the galaxies would be the winning tickets, and there are only 2 trillion of them spread across a volume so large that most of it will never see a galaxy at all. There is a deeper implication here. The environments where galaxies form, where stars ignite, where planets coalesce and life might emerge, are not just rare. They are tied to the structure of the voids. Galaxies do not form randomly. They form along filaments, because that is where the matter is. The filaments are highways, channels carved by gravity where gas can flow, collapse, and ignite. The voids are deserts. Not because they are hostile, but because they are empty. There is no gas to collapse, no fuel to make stars, no raw material to build anything. A galaxy inside a void is not impossible, but it is extremely unlikely. And even if one did form somehow, it would be isolated, cut off from the flows of gas and the interactions with neighboring galaxies that drive star formation and evolution in denser regions. It would be a lonely, quiet place, slowly exhausting its fuel with no prospect of resupply. Life, if it exists elsewhere in the universe, almost certainly exists in the filaments, not in the voids. There is nothing in the voids to support it. No stars, no planets, no chemistry. Just cold, empty space and the faint glow of the cosmic microwave background, radiation left over from the Big Bang, stretched into wavelengths so long that it barely registers as heat. The voids are not hostile in the way a black hole is hostile. They do not crush you or tear you apart. They are hostile in a quieter way. They offer nothing, no resources, no energy, no prospects, just distance, endless, untraversable distance, separating you from anything that might resemble home. The voids are the majority of the universe by volume, and they are uninhabitable, not because conditions are harsh, but because there are no conditions, just absence. 80%. That number is not an approximation, it is a measurement built from millions of data points collected by telescopes and surveys over decades. The Sloan Digital Sky Survey mapped the positions and redshifts of hundreds of thousands of galaxies, building a three-dimensional picture of the cosmic web that covers a significant fraction of the northern sky. Other surveys, like the 2-degree field galaxy redshift survey and the dark energy survey, filled in other regions. Computer simulations running on supercomputers using the known laws of physics and the measured properties of dark matter and dark energy reproduced the structure almost perfectly. The simulations show the same thing the observations do. Matter clumps into filaments, voids form in between. The voids occupy 80% of the volume. The simulations match the data so closely that there is no longer any doubt. The structure is real, the voids are real, and the ratio is real. The universe is overwhelmingly, structurally, measurably empty. 1 proton per 4 cubic meters. That is the average density of the universe. To put that in perspective, the air you are breathing right now contains about 10 to the 19th molecules per cubic centimeter, 10 to the 19th. A 1 followed by 19 zeros per cubic centimeter. The universe averages 1 proton per 4 cubic meters. A cubic meter is 1,000,000 cubic centimeters, so the universe is less dense than the air around you by a factor of about 10 to the 25 orders of magnitude. The densest regions of the universe, the galaxy clusters, are still less dense than the air you are breathing by a factor of billions. The voids are even emptier by the standards of anything you have ever experienced, anything you could ever experience on Earth. The universe is not just empty. It is incomprehensibly empty. The fact that 2 trillion galaxies exist inside that emptiness does not change the math. The galaxies are tiny islands in an ocean so vast that the islands do not matter to the overall density. The ocean dominates. The ocean is the structure, and the ocean is nothing. This is the part that breaks intuition. You look at pictures of the universe, and you see galaxies everywhere. The Hubble Deep Field, the James Webb images, every poster on every classroom wall, they all show galaxies. Thousands of them, packed into small patches of sky, glowing brightly against the dark. It looks crowded, it looks full. But those images are lies, not intentional lies, lies of omission. They show you the galaxies because galaxies are what telescopes detect. They do not show you the space between the galaxies because there is nothing there to detect. No light, no signal, no data, just emptiness. The images compress billions of light years into a flat picture, and they fill the frame with the few bright objects that happen to be in the field of view. What they do not show you is the scale, the distance between each of those galaxies, the millions and tens of millions of light years of empty space separating every dot of light from the next, the voids stretching behind them, invisible and unrepresented because they do not emit anything a telescope can see. If you want to understand what 80% empty actually means, you have to ignore the pictures. You have to go to the data, the surveys, the redshift measurements, the density maps that plot not just where galaxies are, but where they are not. Those maps tell the real story. And the story they tell is one of isolation. 2 trillion galaxies sounds like a lot until you measure the space they are not filling, until you calculate the volume of the voids and compare it to the volume of the filaments, until you realize that most of the universe, the overwhelming majority of the cosmos by volume, will never see a galaxy, will never host a star, will never support anything resembling structure or complexity or life. The voids are not a bug, they are a feature. They are the inevitable result of gravity acting on an almost uniform distribution of matter over cosmological timescales. You cannot have the filaments without the voids. You cannot have the galaxies without the emptiness. The structure depends on the absence, and the absence is growing. As the universe expands, the voids expand with it. The filaments stay bound together by gravity, but the voids inflate, their interiors stretching, their boundaries moving farther apart. The galaxies along the edges of the voids drift outward, carried by the expansion of space, and the distance between them grows. Over billions of years, the voids will get larger, emptier, and darker. The cosmic web will stretch, the filaments will thin, and the ratio between the volume occupied by matter and the volume occupied by nothing will shift even more dramatically in favor of nothing. The universe is not just 80% empty now, it is becoming more empty with every passing second. And there is no process, no force, no mechanism that will reverse that trend. The expansion is accelerating, the voids are winning, and eventually, on timescales so long that the stars themselves will have burned out, the universe will be almost entirely empty, not almost as in 80%, almost as in everything. The galaxies will be so far apart that light from one will never reach another. The filaments will dissolve, the clusters will evaporate, and all that will remain is space, cold, dark, and expanding forever. But that is billions of years away. For now, the voids are just 80%, just the dominant structure in a universe that has not yet finished pulling itself apart. The galaxies are still here, clustered along the filaments, glowing faintly in the dark. And in a few rare pockets, on a few rare planets orbiting a few rare stars, there are probably creatures looking up at the sky and wondering what it all means, wondering why the universe is the way it is, why the galaxies cluster the way they do, why so much of space is empty. And the answer, when you do the math, when you measure the density and map the structure and add up the volume, is simple. The universe is empty because that is what gravity builds when you give it almost nothing to work with and billions of years to work with it. The voids are not an error, they are the result, and they are everywhere. The voids are everywhere. They dominate the universe by volume, carving out space, leaving islands of light floating in an ocean of darkness. 80% empty. That ratio is measured, confirmed, undeniable. But here is the part that changes everything. The voids are not just large, they are growing, and the mechanism driving that growth is the same force that will eventually separate every galaxy in the observable universe from every other galaxy, leaving each one stranded in its own private void, surrounded by nothing, with no way back and no way forward. That force has a name, dark energy, and it is winning. For most of the 20th century, cosmologists assumed the expansion of the universe was slowing down. Gravity pulls everything together, so the reasoning went. And even though the Big Bang started everything flying apart, gravity should be gradually slowing that motion. Like a ball thrown into the air, it goes up fast at first, but gravity pulls it back, slowing it down until it stops and falls. The universe, everyone assumed, worked the same way. Expanding, yes, but slowing. Eventually, maybe, the expansion would stop entirely and reverse, pulling everything back together into a big crunch, the opposite of the Big Bang. Or maybe the expansion would continue forever, but at a slower and slower rate, asymptotically approaching zero, but never quite stopping. Either way, gravity was supposed to be winning the fight, pulling things back together, slowing the separation. In 1998, two independent teams of astronomers, one led by Saul Perlmutter and the other by Adam Rees and Brian Schmidt, measured the distances to a specific type of exploding star called a Type 1a supernova in galaxies billions of light-years away. Type 1a supernovae are useful because they explode with a consistent peak brightness. If you know how bright they actually are, and you measure how bright they look from Earth, you can calculate how far away they are. The teams used that technique to measure distances to dozens of supernovae in distant galaxies, then compared those distances to the redshifts of the galaxies themselves. The redshift tells you how fast a galaxy is moving away. The distance tells you where it was when the light left. Combine the two, and you can measure how fast the universe was expanding at different points in its history. The data should have shown that the expansion was slowing down. It did not. The data showed the expansion was speeding up, not slowing, accelerating. Galaxies farther away were not just receding faster because they were farther. They were receding faster than the equations predicted, even accounting for distance. Something was pushing them apart. Something was overpowering gravity, not just holding it to a draw, but actively winning, driving the expansion faster and faster over time. That something is dark energy. No one knows what it is. It is not a substance. It is not particles. It is not radiation. It is a property of space itself. Every cubic meter of empty space, every void, every gap between galaxies contains a tiny amount of energy, not much, barely anything. But it is there, and it is constant. As the universe expands, more space gets created. More space means more dark energy. More dark energy means stronger repulsion, a kind of anti-gravity pressure that pushes everything apart. The result is a runaway process. Expansion creates more space creates more dark energy accelerates the expansion. Faster expansion creates even more space, and so on, forever. Dark energy is not just driving the current acceleration, it is increasing in influence over time. Gravity used to dominate. Billions of years ago, when galaxies were closer together, gravity was strong enough to slow the expansion, even reverse it in dense regions, pulling matter together into clusters and filaments. But as space expanded and galaxies moved farther apart, gravity weakened. Its influence drops with distance. Dark energy, on the other hand, does not weaken. It stays constant per unit volume, which means as the universe gets bigger, dark energy gets stronger relative to gravity. At some point in the past few billion years, dark energy crossed a threshold. It became the dominant force. Gravity lost, and from that moment on, the universe stopped slowing down and started speeding up. The acceleration we are seeing now is just the beginning. It will get worse, much worse. Perlmutter, Rees, and Schmidt won the Nobel Prize in Physics in 2011 for that discovery. Not because dark energy was expected, because it was not, because it broke every assumption cosmologists had been working with for decades. Because it meant the universe was not just expanding, it was accelerating, and that changes the fate of everything. If the expansion was slowing down, galaxies that are far away now would eventually stop receding. Over trillions of years, they might even drift back closer. The cosmic web would remain connected, at least in principle, but with dark energy accelerating the expansion, that will never happen. The galaxies are not just moving away, they are moving away faster every second. And past a certain distance, they are moving away faster than light can ever catch up. That distance defines a new kind of horizon, not the edge of the observable universe, the sphere of galaxies whose light has had time to reach us since the Big Bang. A different horizon, a future horizon. The edge of the region we will ever be able to reach, even if we could travel at the speed of light. Think of it this way. Imagine you are standing on a moving walkway at an airport, the kind that carries you along at a steady pace. You are walking forward at your normal walking speed, but the walkway is also moving forward, so you cover ground faster than you would on a stationary floor. Now imagine the walkway speeds up. It starts moving faster than you can walk. You are still walking forward, still trying to reach the end, but the walkway is pulling you backward faster than you can move forward. You never reach the end. You never even get close. You stay in the same place, or worse, you slide backward, farther from your destination with every step. That is dark energy. The walkway is space. You are light, moving as fast as anything can move, and the walkway is accelerating. No matter how fast you move, the destination is receding faster. You cannot catch up. You will never catch up. And the farther away the destination is to start with, the worse the problem becomes. Hubble's law describes the relationship between distance and recession velocity. The law is simple. The farther away a galaxy is, the faster it is moving away from us. Not because the galaxy is flying through space at high speed, because space itself is expanding, carrying the galaxy with it. The formula is V equals h times d. Velocity equals the Hubble constant times distance. The Hubble constant, h, is the rate of expansion measured in kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. The current best estimate for the Hubble constant is somewhere around 70 kilometers per second per megaparsec, though that number is still being argued over. What matters for this discussion is the structure of the equation. Velocity increases with distance. Double the distance, and you double the velocity. Triple the distance, triple the velocity. Keep going, and eventually you hit a distance where the recession velocity equals the speed of light. At that point, light leaving that galaxy right now will never reach us. It will spend eternity trying, moving forward at 186,000 miles per second, but the space between us and the galaxy will be expanding faster than that. The light will stay in place, or worse, it will slide backward, redshifted into longer and longer wavelengths until it fades into invisibility. That distance is the cosmic horizon. It is not a fixed number. It depends on the rate of expansion and how much that rate is accelerating. Current estimates put the horizon at somewhere between 15 and 18 billion light-years from Earth. Galaxies closer than that are reachable, at least in principle, if you could travel at the speed of light and you left right now. Galaxies farther than that are not. They are gone, forever. The light we see from them tonight left when they were closer, before the expansion carried them over the edge. But the galaxies themselves are already beyond the horizon, unreachable, unknowable, cut off from us by the expansion of space itself, and the horizon is shrinking. As dark energy accelerates the expansion, the boundary moves inward. Galaxies that are reachable today will not be reachable a billion years from now. The sphere of the reachable universe is collapsing, and there is nothing anyone can do to stop it. This is not a technological problem. This is not something better engines or faster ships can solve. The expansion of space is a feature of the universe itself, written into the fabric of space-time, driven by a force we do not understand and cannot control. Dark energy is not going away. It is not weakening. It is getting stronger, and every galaxy that crosses the horizon is lost, not destroyed. Not dead, just gone, separated from us by a gap so large that no signal, no probe, no information of any kind will ever cross it again. Most of the galaxies we see tonight are already unreachable, 2 trillion galaxies in the observable universe. Most of them are farther than 15 billion light-years away. Most of them have already crossed the horizon. We can see them because the light we are detecting left when they were closer. But the galaxies themselves, at this exact moment, are beyond the edge. Sending a signal to them would be pointless. The signal would never arrive. Even traveling at the speed of light, it would spend eternity chasing a destination that is receding faster than it can move forward. The light from those galaxies will keep arriving for a while. Billions of years, maybe longer, but eventually it will stop. The wavelength will stretch so much that it redshifts out of detectability. The galaxy will fade from view, and once it is gone, it is gone. No future observation will ever see it again. No future civilization, no matter how advanced, will ever detect a single photon from that galaxy. It will be as if it never existed. Here is the loneliest part. The local group, the small cluster of galaxies that includes the Milky Way, Andromeda, and about 80 smaller galaxies, is gravitationally bound. The galaxies in the local group are close enough and massive enough that gravity holds them together. The expansion of space is happening, but within the local group, gravity dominates. The galaxies orbit each other. Andromeda is moving toward us, not away. In about 4 billion years, it will collide with the Milky Way. The two will merge, their stars scattering and reforming into a single large elliptical galaxy. The rest of the local group will follow, eventually coalescing into one enormous structure. That structure will remain bound. It will not expand. It will be an island, a single gravitationally bound system floating in an expanding ocean of space. And as the universe continues to accelerate, that island will become more and more isolated. The nearest large galaxy cluster, the Virgo cluster, sits about 50 million light-years away. It contains roughly 2,000 galaxies, far more than the local group. Right now, Virgo is still visible. We can see its galaxies, measure their redshifts, study their properties, but Virgo is receding. The space between the local group and the Virgo cluster is expanding. Virgo is not gravitationally bound to us. It is part of a larger structure called the Virgo supercluster, which includes the local group as an outlying member. But the supercluster itself is not bound. It is too large, too spread out. Gravity cannot hold it together. Over the next few 100 billion years, as dark energy continues to accelerate the expansion, Virgo will drift farther and farther away. Its galaxies will redshift, first into the infrared, then into the microwave, then into wavelengths so long that no telescope will be able to detect them. Eventually, Virgo will disappear, not because it was destroyed, because it moved beyond the horizon. And once it is gone, no future observer in the local group will ever see it again. The same thing will happen to every other galaxy cluster, every supercluster, every filament in the cosmic web. One by one, they will drift over the edge, carried away by the expansion of space, their light stretching into undetectable wavelengths, their information severed from ours forever. In a few 100 billion years, the night sky as seen from the remnants of the Milky Way will look almost empty. A handful of nearby galaxies, the ones that merged with us or are close enough to remain gravitationally bound, and nothing else. No distant clusters, no filaments, no cosmic web, just a few islands of light surrounded by darkness, and the darkness will be absolute. Not the darkness of a void with a few scattered galaxies, the darkness of a universe where every other structure has receded beyond the horizon and vanished. A future observer in that universe will look up and see almost nothing. They will measure the expansion and find that the universe is accelerating, but they will have no way to know what it is accelerating away from. The evidence, the galaxies, the clusters, the cosmic web, all of it will be gone, erased not by destruction, but by distance. This is the ultimate fate of the universe under dark energy, isolation. Not heat death, not a big crunch, not some dramatic ending, just separation. Every gravitationally bound structure, every galaxy cluster, every local group, drifting alone through an expanding void, watching as everything else disappears over the horizon. The stars in those galaxies will continue to burn for trillions of years. Planets will orbit them. Life, if it exists, will continue, but the sky will be empty. No neighbors, no distant light, no evidence that anything else exists beyond the small island of galaxies held together by gravity. The universe will not end in fire or ice. It will end in loneliness. Each island stranded in its own bubble of space, expanding forever, with no way to reach anything else and no reason to believe anything else is still there. That fate is not theoretical. It is not speculative. It is the direct consequence of the measured acceleration of the universe and the measured strength of dark energy. The only way it does not happen is if dark energy changes, if it weakens or reverses or behaves differently billions of years from now than it does today. There is no evidence for that, no model that predicts it, no reason to think it will happen. Dark energy is a property of space. As long as space exists, dark energy exists. And as long as dark energy exists, the expansion will accelerate, the horizon will shrink, the galaxies will disappear, and the islands will drift alone. Now consider what this means for travel, for exploration, for the possibility of ever reaching another galaxy. Even if you could build a ship that travels at the speed of light, which you cannot because physics does not allow it, most galaxies are already out of reach. You could leave today, traveling at 186,000 miles per second, and you would spend billions of years crossing empty space, only to find that your destination has moved farther away than when you started. The gap would widen, the galaxy would recede, you would never arrive. And even the galaxies that are still within the horizon, the ones you could theoretically reach if you left right now, are so far away that the journey would take billions of years. The Andromeda Galaxy is 2.5 million light-years away. Traveling at light speed, the trip would take 2.5 million years. The nearest large galaxy cluster, Virgo, is 50 million light-years away. 50 million years at light speed, one way. No return trip, no way to send a signal back. No guarantee that the galaxy you are traveling toward will still be there when you arrive, because the universe will have expanded, the cluster will have evolved, and the stars you are aiming for may have burned out or been ejected from their host galaxy in a collision. Intergalactic travel is not just impractical, it is impossible, not because we lack the technology, because the universe does not allow it. The speed of light is the ultimate speed limit. Nothing with mass can reach it. The faster you go, the more energy it takes to accelerate further, and the curve is asymptotic. You can get close, 99% of light speed, 99.9%, 99.99%, but you can never reach 100. And even if you could, even if you somehow built a ship that could sustain light-speed travel for millions of years, crossing the void between galaxies at that speed, the expansion of space would still defeat you. The destination would recede, the journey would take longer than planned. And by the time you arrived, assuming you arrived at all, the universe you left behind would have changed beyond recognition. Billions of years would have passed, stars would have died, civilizations would have risen and fallen. The galaxy you came from would have merged with others, its shape unrecognizable, its position in space shifted by the ongoing dance of gravity and expansion. You would be a traveler from a universe that no longer exists, arriving at a destination that barely resembles the place you aimed for, and you would have no way back. This is the prison, not a cell with walls. A prison made of distance and time, enforced by the expansion of space and the speed of light. The bars are invisible but unbreakable. The galaxies are there, visible in telescopes, glowing in the night sky, tantalizingly close by cosmic standards, millions of light years, billions. Numbers you can write down and say out loud, but those numbers are also barriers. Distances so large that crossing them is not a matter of better technology or more advanced engineering. Crossing them is forbidden by the structure of space-time itself. The universe is not a place you can explore in the way you explore a planet or a solar system. It is a place you can observe, you can look, you can measure, you can photograph, but you cannot go there, not to most of it, not to the places that matter, not to the galaxies beyond the horizon, not to the clusters drifting away, not even to Andromeda, realistically, because the time it would take to reach it is longer than human civilization has existed. The universe is a museum you can see but never enter, and the exhibits are drifting farther away every second. Dark energy is the reason. Dark energy is the force pulling the prison walls farther apart, making the distances larger, the isolation deeper, the prospect of escape more hopeless. And dark energy is not slowing down, it is speeding up. The universe was not always like this. Billions of years ago, before dark energy became the dominant force, galaxies were closer together, the cosmic web was denser, the voids were smaller. Gravity was still losing the fight, but it was losing slowly. There was time for galaxies to interact, to merge, to exchange matter and information. The early universe was a more connected place, not crowded, not by any standard a human would recognize, but more connected than it is now. The filaments were thicker, the clusters were tighter, the voids had not yet inflated to the sizes they are today. If you had been around 10 billion years ago, looking up at the night sky from a planet in some distant galaxy, you would have seen more neighbors, more light, more structure. The universe was younger, denser, and less lonely. That was then. This is now. Dark energy has taken over. The voids are growing. The filaments are stretching. The clusters are drifting apart. And the process is irreversible. There is no going back. No way to compress the universe, to pull the galaxies closer together, to undo the expansion. The arrow of time points in one direction, forward, toward greater separation, greater isolation, greater emptiness. The universe is becoming a lonelier place with every passing second, and that trend will continue for as long as dark energy dominates, which is to say, forever. So where does that leave us? Here, in the local group. On a planet orbiting a star in the outer arm of a spiral galaxy that is slowly falling toward Andromeda, surrounded by about 80 other galaxies, most of them small, most of them faint, held together by gravity in a bubble about 10 million light-years across. That bubble is our cosmic island, the only piece of the universe we will ever have meaningful access to, the only region where travel between galaxies is even theoretically possible, though still absurdly difficult and time-consuming. Everything beyond the local group, everything farther than a few million light-years, is effectively gone. Visible, yes. Reachable, no. We can see Virgo, we can photograph its galaxies, we can measure their redshifts and masses and ages, but we will never go there. We will never send a probe. We will never receive a signal from a civilization that might exist in one of those galaxies. The distance is too great. The expansion is too fast. The gap is unbridgeable. That is the isolation. That is the expanding abyss, not a poetic metaphor. A physical reality enforced by the laws of physics and the measured acceleration of the universe. We are stranded on an island, watching as the rest of the cosmos drifts over the horizon and disappears. The ocean around us is growing, the other islands are receding, and there is no boat, no bridge, no way across, just distance. Endless, growing, insurmountable distance. The universe is not a place to explore, it is a place to observe from a distance, knowing that most of what you see is already gone. Already beyond the edge, already separated from you by a gap that will only widen with time. 2 trillion galaxies, and we are stuck with the few dozen that happen to be close enough to remain bound by gravity. The rest are lost, not destroyed, just gone, and they are never coming back. So dark energy is pulling the universe apart. The voids are growing, The galaxies are drifting over the horizon one by one, carried away by the expansion of space at speeds we can never match. Eventually, in a few 100 billion years, every structure beyond the local group will disappear from view, leaving us stranded on a cosmic island with no neighbors, no context, and no way to know what lies beyond the edge. That is the future. Isolation, loneliness. A universe so empty that future observers will look up at the sky and see almost nothing, with no evidence that anything else ever existed. But that is not now, that is not today. Right now, in this moment, in this narrow window of cosmic time, we are here. Sitting on a planet that should not exist, orbiting a star that took billions of years and countless generations of earlier stars to build, in a galaxy that happened to form in one of the few places in the universe where complexity and structure could survive long enough for something like us to notice. The odds of that are so lopsided, so ridiculously stacked against our existence, that the fact you are reading this right now should feel like the punchline to a joke the universe has been setting up for 14 billion years. And yet here we are, not scattered atoms drifting through a void, not frozen gas in the emptiness between galaxies, here, alive, aware, looking up at the sky and realizing, slowly, just how improbable the whole thing is. Let's start with the obvious. We live in a galaxy, not in a void, not in the empty 80% of the universe that contains almost nothing. We live in the Milky Way, a spiral galaxy sitting in the densest 20% of the cosmos, the part where matter actually collected into something resembling structure. That alone is a statistical fluke. If you picked a random point in the observable universe, 8 times out of 10 you would land in a void, a region hundreds of millions of light years across with almost no galaxies, no stars, no planets, and no prospects for anything interesting ever happening. We did not land there. We landed here, in a galaxy, in a region of space where gas could collapse, where stars could form, where the conditions for complexity existed and persisted for billions of years. The first filter, the first gate you have to pass through to get from the Big Bang to a planet capable of supporting life, is location. You have to be in one of the filaments, one of the dense regions, one of the places where gravity won and matter stuck around long enough to build something. Most of the universe fails that test. We passed it without even trying. But being in a galaxy is not enough. Galaxies come in different shapes, different sizes, different levels of chaos. Not all of them are friendly. Elliptical galaxies, the smooth football-shaped collections of old stars that dominate the centers of galaxy clusters, are mostly dead. They ran out of gas billions of years ago. Star formation shut down. What remains is a population of ancient red and yellow stars, slowly aging, with no new generations to replace them when they burn out. You could have a planet in an elliptical galaxy. Planets probably exist there. But the environment is static, stable, yes, quiet, yes, but also sterile in the sense that nothing new is happening. The chemistry is fixed. The elemental abundances are what they were billions of years ago, and they are not changing. Life, if it requires a certain mix of elements, a certain balance of carbon and oxygen and nitrogen and phosphorus, might struggle in a place where that mix was set in stone before the galaxy even finished forming. Irregular galaxies, the messy asymmetric collections of stars and gas that result from collisions and gravitational disturbances, are the opposite problem. They are active, too active. Star formation happens in bursts, driven by waves of compression as gas clouds slam into each other during mergers. Those bursts produce massive stars, and massive stars live fast and die young, exploding as supernovae that flood their surroundings with radiation. A planet in an irregular galaxy might survive for a while, orbiting quietly in some calm corner. but the odds of a nearby supernova sterilizing the surface increase dramatically in an environment where stars are forming and dying at chaotic rates. Stability matters. Life, at least life as we understand it, requires time. Billions of years of relatively stable conditions where chemistry can do its slow, patient work, building complexity one molecule at a time. Irregular galaxies do not offer that. They are construction sites. Dangerous, unpredictable, and prone to sudden catastrophic events that wipe the slate clean. That leaves spiral galaxies, the flat rotating disks with arms that curl outward from a central bulge, galaxies like the Milky Way. Spirals are the Goldilocks option, not too dead, not too chaotic. They are still making stars, pulling in gas from their surroundings, collapsing clouds in the outer arms where conditions are right. But the star formation is measured, steady, the kind of process that unfolds over millions of years rather than erupting all at once. Spirals also have structure. The arms are not random, they are density waves, regions where gas piles up temporarily as it orbits the galactic center, triggering bursts of star formation as it passes through. A star in the outer arm of a spiral galaxy spends most of its time in relatively empty space, far from the dense core where interactions are frequent and radiation levels are high. It dips through the spiral arms every few 100 million years, experiences a brief period of increased density and nearby star formation, then moves back out into the quieter regions. That rhythm, that slow oscillation between crowded and empty, might be exactly what life needs. Enough activity to keep the chemistry interesting. Enough calm to let complexity build without getting destroyed. The Milky Way is a spiral, a large one by galactic standards, roughly 100,000 light-years across, containing somewhere between 2 and 400 billion stars. Our Sun sits about 26,000 light-years from the center, out in a minor arm called the Orion Spur, tucked between two larger arms, the Sagittarius arm and the Perseus arm. The location is quiet, not too close to the core, where the density of stars increases the odds of close encounters, and the radiation from the central supermassive black hole creates a hostile environment. Not too far out in the halo, where the density drops so low that star formation barely happens, and the galaxy starts blending into the emptiness beyond. We are in the suburbs, the safe zone, the region where stars form at a reasonable rate, where heavy elements are abundant enough to build rocky planets, and where the environment is stable enough that a planet like Earth can orbit for 4.5 billion years without getting vaporized, irradiated, or ejected into interstellar space by a passing star. That stability is not an accident. It is a feature of where we are and when we are. The Milky Way is old, not as old as the universe, but old enough that it has gone through multiple generations of star formation. The first stars, the ones that formed when the galaxy was young, were made almost entirely of hydrogen and helium. No carbon, no oxygen, no silicon or iron or any of the heavier elements that make up planets and, eventually, life. Those elements did not exist yet. They had to be built inside stars, fused together in the cores of massive suns, then scattered into space when those stars exploded. The second generation of stars formed from gas clouds, enriched by the death of the first generation. They had more heavy elements, but still not much, a trace amount. Enough to maybe form a few small rocky planets, but not enough to build a rich, complex chemistry. The third generation had more, the fourth more still. Every generation of stars that lived and died added to the reservoir of heavy elements floating around in the galaxy's gas clouds, slowly building up the elemental diversity that makes planets like Earth possible. The Sun is a third or fourth generation star, maybe later. Astronomers call it a population 1 star, which is confusing because population 1 is actually the youngest category. The naming convention is backwards. Population 3 stars are the first generation, massive and short-lived, made of primordial hydrogen and helium. Population 2 stars are the second generation, smaller and longer-lived, with a tiny fraction of heavy elements. Population 1 stars, like the Sun, are the latest generation, formed from gas that has been cycled through multiple rounds of stellar death and rebirth, enriched with carbon and oxygen and nitrogen and all the other elements that show up in the periodic table past helium. The Sun is about 71% hydrogen, 27% helium, and 2% everything else. That 2% is what matters. That is the carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood. Every atom heavier than helium in your body was forged inside a star that died before the Sun was born. You are made of recycled stardust. That is not a metaphor. That is a direct consequence of where and when you exist in the history of the galaxy. The Milky Way had to be old enough to build up that reservoir of heavy elements before the Sun could form. If the Sun had formed a few billion years earlier, when the galaxy was younger, the gas cloud it collapsed from would have been too hydrogen-rich, too metal-poor, in the astronomer's sense of the word, where metal means anything heavier than helium. The planets that formed around a younger Sun would have been smaller, icier, lacking the rocky cores and thick atmospheres that make a planet like Earth possible. Life, if it could start at all, would have had a harder time, maybe an impossible time. The chemistry would have been too limited. The building blocks too scarce. Timing matters. We are here now, in this moment, because the Milky Way spent billions of years preparing the raw materials we are made of. If we had shown up earlier, the universe would not have been ready. If we show up much later, billions of years from now, the galaxy will have exhausted most of its gas. Star formation will slow to a trickle. The spiral arms will fade. The Milky Way will start its long, slow decline into something quieter, emptier, less capable of building new worlds. There is a window, a stretch of cosmic time when conditions are right, and we happen to be living in it. Now zoom out. The Milky Way is part of the local group, a small cluster of about 80 galaxies held together by gravity. The local group is part of a larger structure called the Virgo supercluster, a collection of galaxy groups and clusters stretching across about 100 million light-years. The Virgo supercluster is part of an even larger structure called the Laniakea supercluster, a network of filaments and clusters spanning 500 million light-years. At every level, we are sitting in a region of the universe where matter collected, where gravity won, where the density was high enough to build galaxies, clusters, superclusters, and the vast web of structure that connects them. If we lived in a void, none of this would exist. No Milky Way, no Sun, no Earth, no us. The voids are not hostile, they are just empty. There is nothing there to work with, no gas to collapse into stars, no stars to forge heavy elements, no heavy elements to build planets. The voids are deserts, and deserts do not grow forests. We are on an island, not just the Milky Way, the local group. The entire gravitationally bound collection of galaxies that will remain connected even as the rest of the universe expands and drifts away. That island is our cosmic address, the only part of the universe we will ever have meaningful access to. And within that island, we are sitting in one of the few places where all the conditions lined up. A stable spiral galaxy, a location in the outer arm where radiation levels are low and stellar encounters are rare. A star that formed late enough to inherit a rich supply of heavy elements. A planet at the right distance from that star, with the right mass, the right atmosphere, the right magnetic field to shield the surface from radiation. Liquid water, a stable climate. 4.5 billion years of relative peace, punctuated by the occasional asteroid impact or volcanic eruption, but nothing catastrophic enough to sterilize the surface permanently. All of that had to happen, in sequence, over billions of years, for you to be here reading this. And the overwhelming majority of the universe, the 80%, that is voids, and the significant fraction of the remaining 20%, that is too chaotic or too dead or too far from the filaments, never had a chance. The island universe metaphor is not new. Edwin Hubble used it in the 1920s when he proved that Andromeda was a separate galaxy, not a nebula inside the Milky Way. He called galaxies island universes, isolated systems floating in an ocean of empty space, each one a self-contained collection of stars and gas with its own history and structure. The metaphor was poetic then. Now it is literal. Galaxies are islands. The local group is an island. And as the universe expands, the ocean between the islands is growing. The other islands are drifting away. In a few 100 billion years, we will be alone, surrounded by darkness, no neighbors, no distant light. Just the few dozen galaxies that gravity held together, orbiting each other in a bubble about 10 million light-years across, with nothing beyond that bubble but the endless expansion of space. But we are not alone yet. Not today. Right now, we can still see the other islands. 2 trillion galaxies scattered across the observable universe, each one containing billions or trillions of stars, each star potentially hosting planets, each planet potentially harboring the chemistry that could, maybe, given enough time and the right conditions, build something alive. The numbers are staggering. If even a tiny fraction of those stars have planets in the habitable zone, the region where liquid water can exist on the surface, you get billions of potentially habitable worlds. If even a tiny fraction of those worlds develop life, you get millions of biospheres. If even a tiny fraction of those biospheres develop intelligence, you get thousands of civilizations. The math is overwhelming. The universe should be full of life, full of signals, full of evidence that we are not the only ones who figured out how to look up at the sky and wonder what is out there. And yet we see nothing, no signals, no megastructures, no signs of industrial-scale activity reshaping stars or galaxies, no radio transmissions, no laser pulses, no artifacts drifting through the solar system. The universe is silent. Not quiet in the sense that we have not listened carefully enough. Silent in the sense that every search, every survey, every attempt to detect a signal from another civilization has come up empty. That silence has a name, the Fermi paradox. Named after physicist Enrico Fermi, who asked the question in 1950 during a lunch conversation at Los Alamos. If the universe is so large, if there are so many stars and so many planets, where is everybody? Why are we not seeing them? Why are they not here? The galaxy is billions of years old. If another civilization had developed even a few million years before us, they would have had time to spread across the entire galaxy. We should see evidence of them. Probes, colonies, Dyson spheres harvesting the energy of stars. Something, anything. But we see nothing. There are dozens of proposed solutions to the Fermi paradox. Maybe life is rarer than we think. Maybe the jump from simple chemistry to self-replicating organisms is so improbable that it only happens once in a trillion star systems. Maybe intelligence is the bottleneck. Life might be common, but most of it stays simple. Bacteria, algae, nothing that builds telescopes or asks questions. Maybe technological civilizations destroy themselves. Nuclear war, climate collapse, runaway artificial intelligence, any number of catastrophes that wipe out a species shortly after it develops the tools to detect others. Maybe they are out there, but they are not broadcasting. No signals, no megastructures, just quiet civilizations living on their planets, content with their islands, uninterested in shouting into the void. Maybe the distances are too large. Even if there are thousands of civilizations in the Milky Way, the average distance between them could be thousands of light years. A signal from the nearest civilization might still be in transit, crossing the gap at the speed of light, decades or centuries away from reaching us. We would not know they exist until the signal arrives. And if they are listening for us, they would not know we exist until our signals, the radio and television transmissions that have been leaking into space since the 1930s, reach them. A two-way conversation would take thousands of years. One message sent, thousands of years of silence, one reply received. Thousands of years later, another message. That is not a conversation. That is a letter written to someone you will never meet, hoping someone centuries in the future will read it and care enough to respond. Or maybe we are alone, not alone in the universe, which is too large for that to be statistically likely, but alone in our galaxy, alone in the local group, alone on our cosmic island. The other islands, the other galaxies, might have their own civilizations, their own histories, their own versions of this same story, but we will never meet them. The distances are too large, the expansion is too fast, the gaps between the islands are unbridgeable. If there is a civilization in Andromeda, 2.5 million light-years away, we will never know. They will never know about us. The light from Earth, carrying the faint signature of our existence, will take 2.5 million years to reach them. By the time it arrives, we might be gone. Extinct, evolved into something unrecognizable or simply quiet, no longer broadcasting signals into the void. And even if we are still here, even if they receive the signal and send a reply, that reply will take another 2.5 million years to reach us. 5 million years, round trip. Longer than humans have existed as a species, longer than most species survive before going extinct or evolving into something else. Intergalactic communication is not just difficult, it is effectively impossible. So we are left with this, a single planet orbiting a single star in the outer arm of a spiral galaxy, on a cosmic island that will remain isolated for as long as the universe continues to expand. Surrounded by 2 trillion galaxies, most of them already beyond reach, drifting over the horizon one by one as dark energy pulls them farther away. We can see them, we can photograph them, we can measure their distances and masses and ages, but we cannot reach them, we cannot visit them. We cannot send a probe, a signal, or even a postcard. The universe is vast, but it is also a prison, a beautiful, awe-inspiring prison, where the bars are made of distance and the locks are made of time. And yet, here we are, against the odds, in defiance of the emptiness. Life found a way to start on this planet, to survive for billions of years, to evolve into something capable of looking up at the sky and understanding, even partially, what it is looking at. That should not have happened. The universe is not set up to favor life. It is set up to favor emptiness. 80% voids, 20% filaments and clusters, a tiny fraction of that 20% containing stable galaxies, a tiny fraction of those galaxies sitting in the right kind of environment. A tiny fraction of stars in those galaxies forming at the right time with the right mix of elements. A tiny fraction of those stars hosting planets in the habitable zone. A tiny fraction of those planets developing life. A tiny fraction of that life becoming complex. A tiny fraction of that complex life becoming intelligent. Stack up all those filters, all those improbable steps, and the odds of you being here should be so small that the universe could run for trillions of years and never produce another example. And yet you exist, not as a hypothetical, not as a statistical prediction, as a fact, a physical, undeniable, breathing fact sitting on a planet that spent 4.5 billion years preparing the conditions for your existence. That is the wonder. The universe is mostly empty, mostly hostile, mostly indifferent to whether life happens or not. But in this one corner, on this one island, in this one brief window of time, it did. Life happened, complexity happened, consciousness happened, you happened, and you are aware of it. You can look up at the night sky and see the Milky Way stretching across the darkness, knowing that every star you see is part of the same galaxy, the same structure, the same cosmic island that made you possible. You can point a telescope at Andromeda and see another island 2.5 million light-years away, knowing that the light you are detecting left that galaxy before humans existed, before anything resembling a human existed, and it has been traveling through empty space ever since, crossing the void to arrive at your eye tonight. You are seeing the past, you are seeing distance, you are seeing isolation, and you are understanding it. That capacity, that awareness, is so rare, so improbable, so cosmically unlikely, that it almost justifies the entire history of the universe. 14 billion years of expansion, structure formation, star death, element creation, all of it leading to this moment. You, here, now, aware, and also terrified. Because the same understanding that makes you feel wonder also makes you feel small. The universe is incomprehensibly large, the distances are unbridgeable, the voids are growing, the galaxies are drifting away. And we are stuck here, on this island, with no way off and no neighbors close enough to call. The loneliness is structural, built into the fabric of space-time, enforced by the speed of light and the acceleration of the expansion. We are not alone because we failed to find others. We are alone because the universe is designed, not intentionally but structurally, to keep everything isolated, to separate islands by distances so vast that crossing them is not just impractical but impossible. The terror is not that we might be the only life in the universe. The terror is that even if we are not, even if there are billions of other civilizations scattered across the cosmos, we will never meet them. We will never know they exist. We will spend our entire existence on this island, looking out at the ocean, watching the other islands drift over the horizon, knowing that the gap is widening and there is nothing we can do to stop it. That is where we are. That is our cosmic address. A rare confluence of conditions on a planet that should not exist, in a galaxy that formed in one of the few places where structure could survive, on an island that will remain isolated as the universe expands and everything else disappears. We are lucky. Impossibly, absurdly lucky. But we are also trapped, and the trap is not cruel. It is just large, so large that escape is not a matter of effort or technology. It is a matter of physics. The universe will not let us leave. It will let us look. It will let us measure. It will let us photograph and catalogue and wonder, but it will not let us go. And maybe that is enough. Maybe the fact that we can look, that we can understand, that we can sit on this island and map the ocean and know what lies beyond, even if we cannot reach it, maybe that is the point. The universe did not have to produce observers. It did not have to build complexity or consciousness or anything resembling a question. It could have remained a sea of hydrogen, slowly cooling, slowly expanding, with no stars, no planets, no life, no one to notice. But it did not. It produced us. Improbably, impossibly, against all odds. And we are here now, on this island, in this moment, looking up at the sky and realizing just how far the ocean stretches. That realization, that awareness, is the most extraordinary thing the universe has ever done. And it happened here, on this planet, in this galaxy, on this island. The only island we will ever know. The question is, what do we do with that knowledge? Do we accept the isolation and focus on the island, exploring every corner of the local group, mapping every star, every planet, every moon within reach? Or do we keep looking outward, keep searching for signals, keep hoping that somewhere in the 2 trillion galaxies scattered across the observable universe, someone else is looking back? The universe will not answer that question for us. It will just keep expanding. The voids will keep growing. The galaxies will keep drifting away, and we will keep sitting here on this island, wondering what lies beyond the horizon and whether anyone out there is wondering the same thing. We are stuck on an island. That is the conclusion. That is the result of 14 billion years of cosmic evolution, structure formation, galaxy assembly, and the slow, patient work of gravity pulling matter together into the few regions where complexity could survive. We live in the Milky Way, part of the local group, sitting in the densest 20% of the observable universe, surrounded by 2 trillion galaxies we can see but will never reach. The voids occupy 80% of the volume. Dark energy is pulling everything apart. The horizon is shrinking. And the overwhelming majority of the cosmos, the vast empty regions that define the universe more than the galaxies ever will, remains almost completely unexplored. Not because we lack curiosity, because we lack tools. The voids are hard to study. They contain almost nothing, and nothing is notoriously difficult to observe. But that is about to change, not because we are building ships that can cross the voids. We are not. We will never build those ships. The distances are too large, the expansion too fast, the physics too unforgiving. But we are building better eyes, better instruments, better ways of seeing the invisible, measuring the unmeasurable, and pulling information out of darkness that for most of human history has given us nothing to work with. The future of cosmic exploration is not about going there. It is about looking harder at what is already here, about reading the signals the voids are sending us, faint and indirect as they are, and using those signals to build a map of the largest structures in the universe. The voids are not empty, not completely, and the things they do contain, the traces of matter and energy and space-time itself, are starting to tell a story. The first tool in that toolbox is gravitational lensing. Einstein predicted it in 1915, but it took decades for astronomers to detect it clearly, and only in the last 20 years has it become a precision instrument for mapping the universe. The idea is simple. Mass bends space-time. Light travels through space-time. So when light from a distant galaxy passes near a massive object, a galaxy cluster, a black hole, even a large cloud of dark matter, the light's path bends. The distant galaxy appears distorted, stretched, sometimes split into multiple images, like looking through a warped glass lens. That distortion is not random. It encodes information about the mass distribution of whatever is doing the bending. Measure the distortion carefully, and you can map the mass, even if the mass is invisible, even if it is dark matter, even if it is sitting in a region where no galaxies shine. Voids do not bend light the way clusters do. They are underdense, not overdense. But that is the point. The absence of mass creates a measurable effect. When light from a background galaxy passes through a void, the path it takes is subtly different from the path it would take through a denser region. The void acts like a lens, but a negative lens, one that defocuses rather than focuses. The distortion is tiny, much smaller than the distortions caused by galaxy clusters, but it is there. And with enough data, enough background galaxies, enough careful measurement, you can detect it. You can map the voids not by looking at what they contain, but by looking at how they affect the light passing through them. Gravitational lensing turns the voids into readable objects. They are still dark. They are still mostly empty, but they are no longer invisible. Several large-scale surveys are already doing this. The Dark Energy Survey, which ran from 2013 to 2019, mapped 300 million galaxies across a significant fraction of the southern sky. The data is still being analyzed, but one of the goals was to measure weak gravitational lensing signals from voids and use those signals to constrain the distribution of dark matter and dark energy. The results are not fully published yet, but early findings suggest the technique works. Voids show up as regions where the lensing signal is weaker than average, exactly as predicted. The more voids you map, the better you can measure the overall structure of the cosmic web, and the better you can test models of how dark energy is driving the expansion. The next generation of surveys will push this further. The Vera-Rubin Observatory, which is scheduled to begin operations in 2025, will map the entire southern sky every few nights for 10 years. It will detect billions of galaxies, far more than any previous survey, and it will measure their shapes and positions with enough precision to build detailed maps of the cosmic web, including the voids. The European Space Agency's Euclid mission, launched in 2023, is doing the same thing from space, mapping the distribution of galaxies and measuring gravitational lensing across a third of the sky. Between Rubin and Euclid, astronomers will have the most detailed three-dimensional map of the universe ever constructed. The voids will be in that map, not as blank spaces, as measurable, quantifiable structures with properties we can study. Sizes, shapes, densities, how they evolve over time, how they connect to the filaments surrounding them. The voids are about to stop being voids in the colloquial sense and start being data. The second tool is the cosmic microwave background. The CMB is the faint glow of radiation left over from the Big Bang, stretched into microwaves by the expansion of the universe, and now arriving at Earth from every direction in the sky. It was emitted about 380,000 years after the Big Bang, when the universe cooled enough for hydrogen atoms to form and light to travel freely for the first time. That light has been traveling ever since, crossing the entire observable universe, and it carries information about the conditions in the early cosmos. Tiny fluctuations in temperature, variations of 1 part in 100,000, correspond to regions that were slightly denser or slightly less dense than average. Those fluctuations are the seeds of everything that came later. The denser regions became galaxy clusters. The less dense regions became voids. The CMB has been mapped in exquisite detail by satellites like COBE, WMAP, and Planck. The data from Planck, released in full in 2018, is so precise that you can see the ripples in the early universe, the patterns of density that gravity would eventually amplify into the cosmic web. But the CMB does not just tell you about the early universe. It also tells you about everything the light passed through on its way to us. When a CMB photon crosses a large structure, a galaxy cluster, or a void, it gets slightly blue-shifted or red-shifted by the gravitational field of that structure. The effect is called the integrated Sachs-Wolf effect, and it is another way to map the voids. Cross-correlate the CMB temperature fluctuations with the positions of known voids, and you can measure how much those voids are affecting the light. The signal is tiny. Measuring it requires combining data from millions of galaxies and the entire CMB sky, but it works. Several studies have already detected the integrated Sachs-Wolf effect from large voids, and the results match predictions. The voids are there. They are affecting the CMB, and we can measure it. Dark matter plays a central role in all of this. Voids are underdense in dark matter, just as they are underdense in ordinary matter. The reason gravity could not pull more matter into the voids is that there was never enough dark matter there to begin with. Dark matter makes up about 85% of all matter in the universe. It does not interact with light, does not emit radiation, does not leave a visible signature, but it has mass, and mass generates gravity, and gravity shapes structure. The cosmic web is a dark matter web first, an ordinary matter web second. The galaxies we see are just traces, bright markers sitting at the densest points in the underlying dark matter distribution. The filaments are dark matter filaments. The voids are dark matter voids. And if you want to understand why the voids are the size they are, why they are growing at the rate they are, you have to understand dark matter. The problem is, we still do not know what dark matter is. We know it exists because of its gravitational effects. We can measure how it bends light, how it holds galaxies together, how it clumps into halos that seed the formation of galaxy clusters. But we do not know what particles it is made of, if it is even made of particles. Dozens of experiments are searching for dark matter, trying to detect it directly by building detectors deep underground where they can shield out other particles and wait for a dark matter particle to collide with an atom in the detector. So far, nothing. No detections, no signal. Just upper limits on how strongly dark matter can interact with ordinary matter, and those limits keep getting tighter. The lack of detection does not mean dark matter does not exist. It means it is even more elusive than we thought. It interacts so weakly with ordinary matter that catching it is like trying to catch a ghost. Dark energy is the other piece of the puzzle. Dark energy is what is driving the accelerated expansion of the universe, pulling the voids apart, pushing galaxies over the horizon, stretching space at a rate that increases with distance. No one knows what dark energy is either. The leading theory is that it is a property of space itself, a kind of vacuum energy that exerts a constant repulsive pressure. Every cubic meter of space contains a tiny amount of dark energy, and as the universe expands, more space gets created, which means more dark energy, which drives the expansion faster. The cycle is self-reinforcing, and it explains the observations. But it does not explain why the amount of dark energy is what it is. The value we measure, the energy density of dark energy, is absurdly small. So small that if you calculate it from first principles using quantum field theory, you get an answer that is wrong by a factor of 10 to the power of 120. 120 orders of magnitude. That is not a rounding error. That is a total failure of the theory. Physicists call it the cosmological constant problem, and it is one of the biggest unsolved mysteries in all of science. Studying the voids might help. The voids are where dark energy dominates most completely. In dense regions, galaxy clusters, the gravitational pull of ordinary matter and dark matter is strong enough to hold things together, resisting the expansion. In voids, there is not enough matter to resist. Dark energy wins. The voids expand faster than the rest of the universe, and by measuring how fast they expand, astronomers can measure the strength of dark energy. Compare that measurement to other methods like supernova distances or the CMB, and you can test whether dark energy is really constant or whether it is changing over time. Some theories predict that dark energy is not constant, that it is a field that evolves as the universe ages. If that is true, the voids should be expanding at a rate that changes over time. Measuring that change would be a huge step forward in understanding what dark energy actually is. Refining our models of large-scale structure is the next step. Right now, cosmologists use computer simulations to model how the universe evolves. You start with the initial conditions, the tiny density fluctuations imprinted in the cosmic microwave background, and you run the simulation forward in time, letting gravity pull matter together into filaments and clusters, while the expansion of space stretches the voids. The simulations reproduce the observed structure remarkably well. They predict the sizes of voids, the distribution of galaxies along filaments, the masses of galaxy clusters, all of it. But the simulations are not perfect. They rely on assumptions about dark matter, dark energy, and the physics of how galaxies form. If any of those assumptions are wrong, the simulations will be wrong too. The voids are a testing ground. Because they are so simple, because they contain so little matter, they are easier to model than dense regions where galaxies interact, merge, and complicate the picture. A void is mostly just dark matter and dark energy. No gas, no stars, no feedback from supernovae or black holes, none of the messy astrophysics that makes galaxy formation so hard to simulate. If you can get the voids right, if your simulation produces voids that match the observed sizes and shapes and expansion rates, you know your model is at least approximately correct. If the voids in your simulation look different from the voids in the data, something is wrong. Maybe your dark matter model is off. Maybe your dark energy model is off. Maybe the initial conditions were not quite right. The voids are a diagnostic tool. They tell you when your model breaks, and the models are already being refined. The latest simulations, running on supercomputers with trillions of particles, are producing voids that match the observations better than ever. The sizes are right, the shapes are right. The distribution of matter inside the voids is right, but there are still tensions. Some of the largest voids, the ones that span 1 billion light-years, are slightly larger than the standard model predicts. That might be a fluke, a statistical outlier. Or it might be a hint that something is missing from the model. Maybe dark energy is slightly stronger than we thought. Maybe the early universe had larger density fluctuations than the CMB suggests. Or maybe there is new physics, something beyond the standard model that we have not accounted for yet. The voids are not just passive features, they are clues, pieces of a puzzle that is still being solved. The philosophical impact of all this is harder to quantify, but no less important. For most of human history, the universe was small. The Earth was the center. The stars were lights on a dome overhead. Then Copernicus moved the Earth out of the center. Galileo showed that the stars were distant suns. Hubble proved that the Milky Way was one galaxy among billions. Each step expanded the scale, pushed humanity farther from the center, made us smaller. And now we know the universe is not just large, it is mostly empty, 80% voids, 20% filaments and clusters. And even in the densest regions, the regions where galaxies actually exist, the space between the galaxies is so vast that the galaxies themselves are just tiny dots scattered across an incomprehensible volume. That realization changes how you see yourself. Not in a depressing way, necessarily, in a clarifying way. You are not at the center of anything. You are not special by location. You are a member of a species that happened to evolve on a planet, that happened to form in a galaxy, that happened to be in one of the few places in the universe where structure could survive long enough for complexity to emerge. The odds of that are vanishingly small. The fact that it happened at all is astonishing, but it is also humbling. The universe does not care about you. It did not build the voids to isolate you. It did not arrange the cosmic web to make exploration difficult. The structure is what it is because gravity and dark energy and the initial conditions of the Big Bang combined in a specific way, and the result is a universe that is mostly empty, mostly dark, mostly indifferent to whether life happens or not. And yet life did happen, here, on this planet, in this galaxy, on this island. That fact, that singular, improbable fact, is worth holding on to. The universe is vast, yes. The voids are enormous, yes. The distances are unbridgeable, yes. But we are here, we exist, we are aware. We can look up at the sky and understand, at least partially, what we are looking at. We can measure the voids, we can map the filaments. We can trace the history of the cosmos from the Big Bang to the present, following the thread of structure formation, element creation, galaxy assembly, star birth, planet formation, and eventually, somehow, the emergence of something that can ask why. That capacity is so rare, so cosmically unlikely, that it might be the most extraordinary thing the universe has ever produced. And it happened here. The ongoing quest is not about conquering the universe. It is not about spreading across the galaxy, or building Dyson spheres, or colonizing other planets. Those might happen. They probably will happen if we survive long enough. But the real quest, the deeper quest, is about understanding, about building better models, about asking better questions, about looking at the voids and the filaments and the 2 trillion galaxies scattered across the observable universe, and asking what it all means, how it all fits together, whether the story we have been telling ourselves for the last century about dark matter and dark energy and the Big Bang is correct, or whether there are pieces missing, gaps in the narrative, surprises waiting in the data. The universe still holds countless mysteries. Dark matter is a mystery. Dark energy is a mystery. The largest voids, the ones that push the boundaries of what the standard model predicts, are a mystery. The Hubble tension, the disagreement over how fast the universe is expanding, is a mystery. The fact that galaxies in the early universe are larger and more massive than they should be is a mystery. Each of these mysteries is a crack in the foundation, a place where the model does not quite fit the data, and those cracks are where the next breakthroughs will come from. Solving them will not be easy. It will take decades, maybe centuries. It will take better telescopes, better detectors, better simulations, and better ideas. But the work is worth doing, not because it will change our daily lives, it will not, but because understanding the universe, really understanding it, is one of the few things that makes us more than just another species of primate scratching out a living on a ball of rock. The Vera Rubin Observatory will map the voids. Euclid will measure the lensing signals. The next generation of CMB experiments will refine the measurements of the integrated Sachs-Wolf effect. The James Webb Space Telescope will keep pushing deeper into the early universe, detecting galaxies that formed when the cosmos was still an infant, and those observations will feed back into the models, refining our understanding of how structure formed, how the first galaxies ignited, how the voids grew. Every new dataset is a step forward. Every new measurement is a constraint on the models. And slowly, piece by piece, the picture will get clearer. But there is a limit. There will always be a limit. The voids beyond the horizon, the regions of space that are receding faster than light, are gone. We will never map them. We will never measure them. The information they contain is severed from us by the expansion of space, and no future technology will change that. The horizon is shrinking. The number of galaxies we can in principle reach is dropping every second as more of them cross the edge and disappear. The universe we can study is getting smaller, not larger. And in a few 100 billion years, when dark energy has finished pulling everything apart, the observable universe will contain almost nothing. Just the remnants of the local group, a single massive galaxy formed from the merger of the Milky Way and Andromeda, and whatever smaller galaxies tagged along, floating alone in an expanding void with no neighbors, no context, and no evidence that anything else ever existed. Future observers in that universe, if any exist, will have a harder time than we do. They will look up at the sky and see almost nothing, a few stars in their own galaxy, and beyond that, darkness. The cosmic microwave background will have redshifted into wavelengths so long that it will be undetectable. The distant galaxies, the filaments, the clusters, all of it will be gone, vanished over the horizon. Those observers will not know the universe is expanding because there will be nothing left to measure the expansion against. They will not know about dark energy because the evidence, the accelerating recession of distant galaxies, will no longer be visible. They will not know about the Big Bang because the CMB, the smoking gun, will have faded into noise. They will be trapped on an island with no map, no history, and no way to reconstruct the story of how they got there. We are lucky, absurdly lucky. We live in a time when the evidence is still here, when the galaxies are still visible, when the CMB is still detectable, when the voids can still be mapped and studied and used to test models of the cosmos. That window will not last forever, but it is open now, and we are using it. So what do we do with that? We keep looking, we keep measuring, we keep building better instruments and asking harder questions. Not because the answers will save us from the isolation, they will not. The voids will keep growing, the expansion will keep accelerating, the horizon will keep shrinking. But understanding that process, mapping it, quantifying it, predicting how it will unfold over the next trillion years, that is the work. That is what separates us from the voids. The voids are passive. They do not observe. They do not measure. They do not ask questions. We do. And as long as we do, as long as we keep pointing telescopes at the sky and pulling data out of the darkness, we are doing something the universe did not have to allow. We are reading the story written into the structure of space-time itself, a story of how matter clumped, how voids formed, how galaxies ignited, and how, in one rare corner of the cosmos, something looked back and understood. The echoes of the void are faint. They are indirect. They are encoded in gravitational lensing signals, in temperature fluctuations in the CMB, in the subtle distortions of light passing through underdense regions. But they are there, and we are learning to hear them. The voids are not silent. They are just speaking a language we are only beginning to understand, and every new observation, every new dataset, every new simulation is a translation, a step closer to fluency. The universe is mostly empty, yes, but the emptiness is not featureless. It has structure, it has history, it has information, and we are going to read it. That is the future of cosmic exploration. Not ships crossing the voids, not colonies on distant planets, just better eyes, better tools, better questions. The voids will never be visited, they will never be crossed, but they will be understood. Mapped, measured, modeled, and used to refine our picture of how the universe works. That might not sound like much compared to the dream of interstellar travel, but it is everything, because understanding is all we have. The voids are growing, the galaxies are drifting away. The island is shrinking, but the data is still arriving. The light is still reaching us, the story is still being told, and we are still here, listening. So here we are, standing on a rock that took 14 billion years to prepare, looking up at a sky that is mostly made of nothing. 2 trillion galaxies scattered across a volume so large that 80% of it will never hold a star, never host a planet, never witness a single moment of complexity or awareness. The voids are not background, they are the structure. The galaxies are decorations, rare and precious, clinging to the edges of an ocean that dominates by sheer emptiness, and yet you exist. Not as a mistake, not as an accident, but as the result of an almost impossibly long chain of events that had to happen in sequence, in the right place, at the right time, with the right ingredients. The universe did not have to build observers. It could have remained hydrogen, cooling and expanding forever, with no one around to notice, but it built you instead, and you are noticing. The distances are terrifying. The isolation is structural. The voids are growing, the galaxies are drifting away, and most of the cosmos is already unreachable, severed from us by the expansion of space itself. We are trapped on an island, watching the horizon shrink, knowing that in a few 100 billion years, the sky will go dark and we will be alone. That is the map. That is the truth written into the fabric of space-time. But the map is not the end of the story, because we can still see it. The evidence is still here. The light is still arriving, and we are reading it, one photon at a time, pulling meaning out of darkness, turning the vast empty spaces into data, into understanding, into something that matters. The universe is mostly void, but the parts that are not, the rare islands where complexity survives, are where everything happens. And one of those islands is here. You are on it, looking up, aware. And that might be the most extraordinary thing the cosmos has ever done. To look outward now is not merely to admire distant galaxies, but to preserve the evidence of a universe that will not always remain visible.